Good evening. So, good evening, everyone. Yes, sir. Rameshwar, that is due to third harmonic current is opposite direction. Okay. That will come in the transient condition. So, we will see again in the some other session. We will see about transient in switching transients in transformer. So, mostly by this month, and we will finish transformer. Second harmonic we are not taking because what is our signal? Symmetrical signals, no? So just like given that point additionally, whenever signal is unsymmetrical, then we have second harmonic also. That is both odd and even harmonics will be there. And in that, which is dominant? Second is dominant. But in all our signals are symmetrical, but non-sinusoidal. That's why only odd harmonics. So the dominant harmonic is third harmonic in this. Okay. That I don't know, Jadoo. Suraj. Protection you will get in already in power system. No? Protection we don't discuss here. Inrush current is transient current in a transformer. We will see that topic again, not now. So there we will see about the inrush current. Okay. So previously we have started non-linearity, effect of non-linearity in single phase transformer. What is the effect? So first of all, I am just recollecting all the points once. Try to remember. Now, due to non-linearity of core, as it is ferromagnetic material, generally, what is the shape of source current? Sinusoidal. Source of current is sinusoidal. If the magnetizing current is sinusoidal, in practical case, due to non-linearity, what is the flux produced? Flat top. If current is sine, flux produced is flat topped or trapezoidal. Then what is EMF induced? Peaky wave. The EMF induced will become peaky wave. But from transformer, what is the EMF required to the loads? Sinusoidal voltages required. So in order to produce sinusoidal EMF, what should be the flux in the core? Sinusoidal, because EMF completely depends on flux in core. The flux must be sine. So to produce a sinusoidal flux, what should be the current in the winding? The magnetizing current in the winding must be peaky wave. Peaky wave. But is peaky wave we are supplying from the source? No. Then how it is generated? In order to get peaky wave, what is required? Third harmonic current should be there. But when third harmonic current will flow? When there is some third harmonic EMF. Otherwise, it cannot flow. So from the source, whatever the current is going, that is always sinusoidal. But due to EMF induced, third harmonic EMF E3 in this, a current I3 is flowing, third harmonic current. Then due to that current, overall current in the winding will become peaky wave. So finally EMF induced is sinusoidal. So what is the current from the source in case of practical transformer? Current drawn. Actually source current sinusoidal, but total input current if you take the sum of these two, fundamental plus third harmonic, that is peaky wave. I mu is peaky wave. Okay, then flux is sinusoidal, EMF also sinusoidal, then that EMF we are applying to loads. Then what is the load current waveform? What is the load current waveform? Suppose if they ask what is the load current waveform, this is sinusoidal only. Why sinusoidal? EMF induced sinusoidal, so current also due to that EMF sinusoidal. only the current taken from the source or input current of this transformer when they are, that is peak wave. Okay, so we have seen this effect of non-linearity in case of single phase transformer. So there is no problem for single phase transformer. Okay, even if you apply whatever sinusoidal voltage source, what is the EMF induced in the winding? Sinusoidal only. So steady state, there is no problem. Okay, now let's see what is the effect of this non-linearity in case of three-phase transformers. Thank you, Jadhav. Right, effect of non-linearity. Effect of non-linearity in three-phase transformer. In three-phase transformers. Three-phase transformers. So in offline classes, it will be still better than this online mode. Generally, in online means some communication gap will be there, no, directly. So we don't have that direct communication. Okay. In three-phase transformer, effect of this non-linearity. So it depends on two things again. In three-phase transformer, it depends on two things. One is type of winding. Type of winding means we have delta connection and star connection in case of three-phase transformers. No, three phases means what? Take three single phases. You need to connect the three single phases either in star connection or delta connection. So we have two connections in three phase. So maybe all of you know in your network theory already you got these relations, star connections, delta connections. Okay, so it depends on type of winding. This non-linearity effect depends on type of winding, whether it is star connected or delta connected. And one more is type of magnetic circuit. What is magnetic circuit means? Transformer core itself magnetic circuit. Okay, in three phase also we have two types. However, we have in single phase two types: core type transformer, shell type transformer. In three phase also we have two types of cores. Here also we call core and shell only, but there are some little additional names are there. We will see what it is. Okay, now effect of non-linearity in three phase transformer depends on two things: type of winding and type of magnetic circuit. But right now we are not seeing both, so we are seeing only type of winding. Once we start three phase transformer, there about that second point I will give you the information. Right now I'm not giving anything about type of magnetic circuit because still it is not completed. Once three phase is started in the magnetic circuit, I will show you how that non-linearity depends on type of magnetic circuit. Okay, only type of winding we are seeing. Okay, right. First type of winding. First, I am considering in the type of winding, we have two connections, delta connection and star connection. Considering star connected winding, star connected winding. Suppose if the three phases are star connected, then how the effect of this non-linearity? So I'm considering mainly primary winding. So in three phase transformer, primary and secondary. However, we have in single phase transformer, primary, secondary, and primary having three phases and secondary also having three phases. Now you can connect the primary and secondary in any way. So what are the connections we have total in three phase transformer? Delta, delta, star, star, delta, star, star, delta. Total four types of connections we have: primary delta, secondary delta, like this, and so on. Okay, now I am considering with respect to primary winding only, because primary we are giving supply, not there. Primary side we are giving supply. So I am considering only the primary winding. One is delta, one is star. Okay. First I considered star connected winding. Let's see. So I'm considering the primary winding is star connected. This is A phase. So three phases A, B, C. I'm taking A phase. It is. Let this is B phase and C phase. Three phases. Okay. Now how to connect these three phases? Let it is A phase, B phase, C phase. How to join three phases? So what it means? Three phase transformer means what? You take three single phase transformer. Transformer A, primary side, secondary side. Capital A, small a. Transformer B, second transformer, single phase transformer, small b. Transformer C. Three single phase transformers we are connecting as a single three phase transformer. For that you need to join these terminals or not? Yes. This A, B, C you need to connect. How to connect? Can you connect whatever the connection you want? Any end you can connect directly? No. Whether you want to connect in delta or if you want to connect in star, anything you should do polarity test. Without that, directly you should not join the winding. Polarity should be marked here. In star connection, we always need to connect the polarities like suppose this is dotted terminal in A phase. This will be dotted terminal in B phase. This will be dotted terminal in C phase. And what is this? Undotted, undotted, undotted. So we need to join similar polarities in case of star connection. We need to join similar polarities in case of star connection. And in case of delta, we will join opposite polarities. So why it is required that I will show you in delta connection. If it is a star, join similar terminals. Now what is this point we call neutral? What is the combination of these 3 points we call neutral point? It is for A phase, B phase, C phase, neutral point in star connection. Okay. Now this star connected winding, I am exciting from a source because we need to give source to primary winding. So source I am connecting. What is the source for this? Three phase generator. So the three phase generator I am taking. This is three phase generator or alternator simply. This is our source of supply. Observe this. A source is applied to star connected winding, then a current will flow. What is the source always? Sinusoidal. The voltage source always applied is what? Sinusoidal only. Now a current will flow in this. What is that current? Magnetizing current, which is responsible to create flux. Now due to that current, what is the shape of current now? What is the shape of current now? Sinusoidal only, no? Because source is sinusoidal. So current is also sinusoidal. Okay. Current, magnetizing current now flowing here is sinusoidal. In all the phases, current will flow. All the phases, current will flow. Because three phases, the current in each phase, magnetizing current in A phase, B phase, C phase, and so on. Okay. Current is flowing. Now, if current is sinusoidal, what is the flux produced? Don't forget the points. The previous yesterday's points, don't forget. What is that? If current is sinusoidal, what is the flux produced? Flat top. What is EMF induced? Peaky wave. Okay, this is one point. And what is other point? If current is peaky wave, what is the flux produced? Sinusoidal. What is EMF induced? Sinusoidal. Remember these 2 points. Never forget this. So now current is from the source sinusoidal. So as sinusoidal current is flowing, whatever the flux produced in each phase, now what is that flux produced? Flat top now. Flat top flux means what? It is non-sinusoidal having odd harmonics. Therefore, the flux produced is flat top phi 1 plus phi 3 plus phi 5 and so on. But only we are taking fundamental and third harmonic, neglecting higher order. No, that is fifth, seventh. We are neglecting, not considering that. So the flux produced is flat top flux. Now, due to that flux, what is the nature of EMF induced? Fundamental flux will cause EMF E1 plus third harmonic flux also will cause EMF E3. Therefore, in each phase, the EMF induced is peaky wave. A phase EMF induced, B phase also EMF induced, C phase also EMF induced. So that is I'm writing here. In A phase, the EMF induced is, how to write voltages in three-phase system? Any one phase we take reference at an angle 0. Then where is B phase? 120 degrees. In three-phase system, the voltages and currents are displaced by how much angle? 120 degrees. So with respect to that, I'm writing A phase E1 at an angle 0. Reference I'm taking A phase 0 plus E3 at an angle 0. Fundamental EMF, third harmonic EMF. Similarly in B phase, E1 at an angle, how much angle it is lagging? Minus 120, because three phases 120 degree displacement, plus E3 at an angle how much? What is the angle made by third harmonics? This is 0 only. So why it is 0? I will show you again, just right. In C phase, E1 at an angle minus 240 plus E3 at an angle 0. Therefore, whenever current is sinusoidal, the flux produced is flat top, which causes EMF in the winding is peaky wave. That is, peaky wave means non-sinusoidal, having fundamental plus third harmonic EMF. Therefore, in each phase we have E1, E3, E1, E3, like this. Now, in delta and star connection, we have phase voltages, line voltages concept. Phase voltage, line voltage. Phase voltage means what? See, this is terminal A, terminal B, terminal B, and this is terminal C. Okay, A, B, C, three phases. Now, A to N we call phase voltage. A to N. This is one phase voltage. Similarly, B to N, and so on. VBN, VCN. Okay, and line voltage means what? Line voltage between any two terminals. If you take voltage VAB is the line voltage, or VBC, this is also line voltage, or VCA, this is also line voltage. VAN, VBN, VCN, these are all phase voltages. Now here one advantage in case of three-phase transformers is, even if current is sinusoidal, flux is flat top, EMF is peaky. Which EMF is peaky wave? Phase EMF or line EMF, or phase voltage or line voltage? Phase voltage means VAN. So what is VAN? This is E1 at an angle 0 plus E3 at an angle 0. Now if you want to find VAB, this is A, this is B. Suppose the voltage between VAB or VAC, anything you can find, anything. VAC it is, VAC. This is called line voltage. Now you try to find one time line voltage. See, try to find line voltage. Next page. VAN is E1 at an angle 0 plus E3 at an angle 0. Similarly, VBN, what is VBN? E1 at an angle minus 120 plus E3 at an angle 0. Third harmonic 0 only. Why it is 0? I will show you again. VCN equal to E1 at an angle minus 240 plus E3 at an angle 0 only. Fundamentals only 120 degree displacement. Third harmonic 0. Okay. Why it is, I will show you with the equations after completion of this. Now, therefore, suppose I need line voltage VAB. VAB I need to calculate. How to find VAB? VAB is nothing but VAN minus VBN. VAN equal to VAB equal to VAN minus VBN. Okay, all of you are aware of this calculation, I think. Calculation of line voltage, phase voltage in star and delta. VAB is the line voltage, nothing but VAN minus VBN. Okay. See how we draw voltages. Let this is A phase voltage VA. Let it is B phase 120 degrees. Let it is C phase. Okay, this is neutral. Now this is VA, VAN. VAN is what? Phase voltage. VBN also phase voltage. VCN also phase voltage. Now, if it is required to find line voltage VAB, how to find VAB? Let VB it is. VAB we need to calculate. VAB means observe. Let us take this VB exactly opposite direction. Exactly opposite. This is minus VB. VA or VIN, both are same. VAN or VBN. Okay. This is minus VB, exactly opposite. Now resultant of these two we call VAB. Resultant of these two. This is VAB. This is VAB resultant. Okay. Now VAB is what? VAN minus VBN. So directly you should know. I no need to write all this. You should know from network analysis all this calculation of line voltages. Okay. Now VAN minus VBN. Let's substitute here. VAN is what? E1 at an angle 0 plus E3 at an angle 0 minus what is VBN? Substitute this one. E1 at an angle minus 120 plus E3 at an angle 0. Okay. Now solve this. E1 at an angle 0 plus E3 at an angle 0 minus E1 at an angle minus 120 minus E3 at an angle 0. Now in this equation, this gets cancelled or not? Yes, E3 cancel. Now E1 at an angle 0 minus E1 at an angle minus 120. So try to find in the calculator by putting your calculators in complex mode, try to find what is this value. Take E1 outside, 1 at an angle 0 minus 1 at an angle minus 120. So try to find in polar form how much it is. So if you calculate this value, you will get root 3 E1 at an angle some 30 degrees. Okay. This is our line voltage. This is our line voltage. Like that, if you find VBC or VCA, you will get same magnitude root 3 E1 only. Maybe some angles will get different. Here you got 30, there you will get some other angle. But anyhow, magnitude is root 3 E1 only in all. If you want to calculate this, VBC, VCA also. Now, what is our observation finally is, see here. The current drawn from the source is sinusoidal, magnetizing current. Then flux produced flat top, EMF induced peaky wave in each phase. So each phase having fundamental EMF, third harmonic EMF. But what is the line voltage? Check. Line voltage, VAB. This line voltage VAB is having only fundamental voltage. Is there any third harmonic voltage in this? No. The third harmonic gets cancelled. Now there is no third harmonic in this. Means what is the shape of line voltage in star connection? Sinusoidal, because only fundamental is there. No third harmonic EMF. So even if you excite from sinusoidal voltage source in practical transformer, if it is star connected or delta connected, also same thing, you will get star or delta. The line voltages are always sinusoidal, whether it is star connection or delta connection, anything. The line voltage is always sinusoidal. No third harmonic EMF in that. But what is the phase voltage? That is having both the fundamental and third harmonic. So right there, clearly all these points first. So take in the figure, completed. Yes. Fifth harmonic is negative. So, right, next page. Next page. Right here. In star connection, the shape of I mu is see, this is one more important observation you should observe here. The neutral, I did not provide any grounding. Neutral is not grounded here. So we have star connection with two cases again. Star is neutral ungrounded and star is neutral grounded. Two cases. two cases we have. So this is ungrounded case. Grounding is not provided. Now after this we will take other case, grounding will provide. When you provide grounding, then we will see what happened. Okay, clearly. No need to confuse in this. So you can write here star connected winding, write in bracket, neutral ungrounded, neutral ungrounded. Okay, case 1 it is. Case 1, neutral ungrounded case. After this we will provide neutral grounding, then we will check what happened again in that. Right here in star connection, the shape of I mu is sinusoidal. Then the flux produced in the core, the flux produced in the core is flat top or trapezoidal shape. We call the flux produced in the core is flat top, and EMF induced in each phase, EMF induced in each phase is peaky wave. Peaky wave. Peaky wave means harmonics, that is E1 plus E3, both will be there. In each phase we have fundamental EMF, third harmonic EMF. Okay, so this is shape of I mu, sinusoidal, flux is flat top, EMF induced is peaky. But in the same case, what is the line voltage? What is the phase voltage shape? Suppose if they ask particularly in any star connection, the phase voltage is dash. So right here, shape of phase voltage, shape of phase voltage, maybe A phase, B phase, C phase, any phase. Shape of phase voltage is what? Peaky wave, peaky wave. Similarly, what is the shape of line voltage? Shape of line voltage. Line voltage is having only fundamental. What is the shape of fundamental? Means sinusoidal. So this star connection, is it suitable for single phase loads directly? No. Why? Single phase. Single phase means phase line to neutral we are taking na voltage. So if you take phase voltage to the load directly, what happened? Peaky wave, na it is. Then your loads will damage. So this star connection is not suitable for single phase loads because the phase EMF is peaky voltage. But what is the shape of line voltage in star connection? Sinusoidal. So it is suitable for loads. Load required a sinusoidal EMF or voltage. So line voltage means three-phase load you can connect. Three-phase load, when you connect, line voltages only will appear across the load, no, not phase voltage. Whenever line voltage appear across the load, then no problem. So finally, this three-phase star connection suitable for line volt. It is suitable for three-phase loads, but not for single-phase loads. Simple. It is suitable for three-phase load, but not for single-phase load. Okay, remember that point. Now we will consider same star connection with neutral grounding. Case 2. Let's see that. Yes. Yes, good. Good. Vishnu, right. Let's see case 2. Same star connection with neutral grounding. With neutral grounding. The same figure, when you provide the star connection with neutral grounding, then what is the shape of current, shape of flux, shape of phase EMF, shape of line EMF? So this is little important. Now maybe most of you may consider that current I mu is peaky wave, but still it is not peaky, sinusoidal only, because one point still I did not said properly. So what is that? Try to understand here. See, this is a star connected winding. primary side of transformer. Now this is excited from a sinusoidal voltage source. This is excited from a sinusoidal voltage source. Okay, supply is given to transformer primary. Then whenever supply given, a current will flow in this. A current will flow, that is magnetizing current initially to create flux in the core. Okay. Now what is the shape of current? Tell me. Neutral, grounded. Neutral is grounded. Neutral, grounded. What is the shape of magnetizing current? Neutral of star connection is grounded. What is the shape of magnetizing current? Sinusoidal. Okay, if current is sinusoidal, what is the flux produced in the core? Flat top. Flux produced in the core is flat top. Flat top means fundamental, both having it is third harmonic. Then what is the EMF induced in each winding, each phase? Peaky wave. The EMF induced is peaky wave. Now that is in each phase we have fundamental plus third harmonic EMF like this, E1 plus E3. So anyhow I'm not writing angles, that is there, E1 plus E3. Okay. Now due to this third harmonic EMF in single phase transformer we have seen source fundamental voltage and EMF fundamental voltage both balance each other. Source voltage and EMF induced fundamental balanced, but this third harmonic is not balanced. Now this third harmonic, what it will try to do? It will cause a current to flow. Now that current here is I3. Current due to third harmonic EMF, current is I3. Similarly in B phase, current is I3, and C phase current is I3. Now as you provided neutral grounding, what happened? As you provided neutral grounding, now this third harmonic current, this third harmonic current, this third harmonic current from three phases, it will come from neutral outside. It will come from a neutral outside as it is grounded. Now this third harmonic current, what is total neutral current? This is IN. Let total neutral current IN equal to 3I3 neutral current. Now this neutral current will circulate or not? Will circulate or not? Tell me. As neutral is grounded, now third harmonic current will circulate or not? No. Yes, good. It won't circulate. It won't circulate because you provided neutral grounding. Okay. Up to here, third harmonic current is coming. Up to the grounding, current is coming. But is there any return path or closed path for the current? No. So in order to provide closed path, you have to provide neutral grounding of source also. Then only it will satisfy. Otherwise, the questions are same as it is previous case. Shape of current. What is shape of current? Sinusoidal. What is shape of flux? Flat top. What is shape of EMF? Peaky wave in each phase. And line voltage is what? Sinusoidal. Just like previous case. So if you provide neutral grounding for only star connected winding, that is not at all enough. You should also provide neutral grounding for source also. Then only, see, now this IN neutral current will take a path through this ground. It is a path through the ground, and this 3I3 will enter here. This 3I3 will enter here. Now this I3, one I3 will go in this direction, one I3 will go in this direction, and other I3 will go in this direction. Now already there is fundamental current previously I mu. Now I3 also flowing through this. Then what is the resultant current? Peaky wave. Now the resultant current is peaky wave because you provided a path to flow the third harmonic currents. Now resultant current is peaky. Now once current is peaky under steady state, what is the shape of flux finally? Sinusoidal. What is EMF induced in each phase? Also sinusoidal. And what is the line voltage? That is always sinusoidal anyhow. Now clear? In the previous case, we are not providing any neutral grounding. So in each case, we have I3 is produced, but no path. Now automatically it will become 0 here because no neutral grounding. That's why I3 cannot flow. But in this case, as neutral is grounded, there is a path for third harmonic current. through this. Grounding should be provided for both winding and source. Then only current will circulate. Current is circulating. Now clear? What is the shape of current after steady state now? Under transient means just started, then I mu sinusoidal, flux is flat top. But finally under steady state operation of this three-phase star connection with a neutral grounding, what is the shape of current? Magnetizing current, peaky wave. Shape of magnetizing current is peaky because I mu is there sinusoidal and I3 also flowing. When fundamental plus third harmonic, what is the resultant current? Peaky wave. I mu is peaky, flux is flat top, flux is flat top. No, flux is what? Sinusoidal. Whenever current is peaky, flux becomes sinusoidal. And EMF is also sinusoidal. So EMF induced in each phase is sinusoidal. Okay. So there is no problem of star connection when you provide neutral grounding along with the source neutral grounded. Okay. Suppose if they given in the question, source is ungrounded, then what is the shape of current? What is the shape of current? Magnetizing current, sinusoidal only, because neutral is not grounded for source. So you should observe carefully this point in the question given. Okay, clear all of you this? Transient means just when you give supply, just for fraction of second. At that time, transient. So, but transient means it will die out after 5 time constants. No? Steady state means after some time when you give supply. Yes. Why E3 is at an angle 0, I will tell. So already given, I said I will show you why third harmonic EMF is at 0 degree. The third harmonic components we call zero sequence components. Zero sequence components. That's why we are writing 0 degree, that is. So how it is 0, I will show you now. Yes. So this is about star connection. So in star connection, what is the shape of magnetizing current with a neutral ungrounded case? Sinusoidal. If I mu is sinusoidal, what is the flux produced in the core? Flat top. Then what is EMF induced in each phase? Peaky wave. But what is the line voltage shape? Sinusoidal, because E3 gets cancelled out when you calculate line voltages. So line voltages always sinusoidal in star connection, whether neutral grounded or ungrounded, any case. Okay. Whenever neutral is grounded, then what is the shape of magnetizing current drawn by the winding, primary winding? Peaky wave, because I mu is there and third harmonic current also circulating. Then what is the shape of flux produced? Sinusoidal, and EMF also sinusoidal. Okay. Okay. So somebody is asking why only I3 is flow towards ground but not magnetizing current. Why it is? Why I mu is not flowing? Because in three phase, what is the sum of voltages? E1 at an angle 0, E1 at an angle minus 120 plus E1 at an angle minus 240. In three phase system, whether it is star or delta, any case, balanced case, always E1 at an angle 0. So voltages are same in every phase. And how they are displaced by 120 degrees, 0, minus 120, minus 240. And if you take the sum of these three, you will get 0. Sum is 0. Then if three currents are coming at one point, what is the sum at that time? 0. Then where is the return path? Then is there any conductor required to take that return? Because return current is 0. There is no current return to the source again here. In three-phase system, in three wires, whatever currents are flowing, they are balanced with 120-degree displacement. The sum of these three currents, if you calculate, it will be 0. Sum 0 means there is no current to be returned again. That's why current I mu will not return to source. That is coming only from each phase, A phase, B phase, C phase. But what is the third harmonic current? Is there any displacement for third harmonic? I3 at an angle 0 in A phase. In B phase also I3 at an angle 0. In C phase also I3 at an angle 0. Then what is the sum of these three? The sum of these three is 3I3. This is not 0. Then that 3I3 should go return. That's why it is coming through neutral grounding and then enters here and again coming. So that's why third harmonic current is circulating. But only I mu will come from source and end at winding. It won't take again return path. Okay, now clear? If source is not grounded, then suppose source is not grounded, remove this. Then how this IN will go to the neutral of source? It cannot enter into this. No? Yes, the third harmonic current cannot circulate. That's why if you want to circulate the third harmonic current, you should provide neutral grounding for source also. Then only that 3I3 will come here and circulates like this. Okay. Magnetizing current is what I mu in the from the starting class, starting day 2, I think, day 2. So there itself I given magnetizing current to create flux in the core. The current which create flux in the core we call magnetizing current. Now that is we are considering here. That is only the responsible for flux creation. And I3 is what? Third harmonic current. Why I3? So I don't know whether in yesterday's class you are present or not. Now if you ask doubt, it will disturb for other people. No? In case 1 here, what happens to I3? See, I3 is there. I3 is there. I3 produced. Here also I3 produced. Here also I3 produced. But now there is total sum here IN equal to 3I3. But is there any path to flow this current continuously up to this neutral and enter here and to continue the path? No, there is no path. So automatically that I3 will become 0 here. I3 cannot flow. If there is no continuous path, what is the current in that circuit? 0. Same thing here. I3 will become 0. In case 2, I3 is taking path, but not here. Okay. So I3 is not flowing. If I3 is not flowing in the winding, what is the shape of current? Only fundamental current. The shape of that fundamental we call sinusoidal. Okay. Okay. Now let's see little bit about the three phases. So why the third harmonic is 0? Oh, I will show you here. Generally in three-phase system, in three-phase system, three-phase system, the voltages and currents are displaced by how much angle? Always 120 degrees. Three-phase system. Now Let us consider the EMF induced in each phase is non-sinusoidal. What is the EMF? In first case, we observed. What is the shape of magnetizing current? Sinusoidal. Then flux produced, flat top. Then what is EMF induced in each phase? Non-sinusoidal. That is we call peaky wave. So let EMF induced in A phase, EA equal to, it is having fundamental, let fundamental E1 sine omega t plus third harmonic E3 sine 3 omega t plus E5 sine 5 omega t plus and so on. Odd harmonics, non-sinusoidal means odd harmonics 1, 3, 5, 7 and so on. But generally we are considering 1 and 3 only, neglecting higher order. So up to 5, let us take up to 5. Like that, this is A phase reference. Next, in B phase also EMF induced. What is that? That is also peaky wave, non-sinusoidal. Then what it is? Fundamental E1 sine omega t minus 120. Why minus 120? A to B phase angle is 120 degrees always, time angle displacement. Plus in B phase third harmonic E3 sine 3 into omega t minus 120. Okay, plus E5 sine 5 into omega t minus 120 plus and so on. Like that in C phase, E1 sine, how much angle it is with respect to A phase? 120 or 240, omega t minus 240 plus E3 sine 3 into omega t minus 240 plus E5 sine 5 into omega t minus 240 plus and so on. Like that seventh harmonic also you can take. Now, if you consider only these fundamental parts, this one, this one, this one, only fundamental EMF we call fundamental. If you consider only fundamental, let us consider this is E1 sine omega t. This is A phase. A phase fundamental EA1, E1 sine omega t. Now E1 B phase fundamental is where E1 sine omega t minus 120. So after 120 degrees we draw. This is B phase fundamental. Let EB1. Like that EC1 again minus 240, it is. This is 120 degrees and this is minus 240 degrees. Okay, EC1 fundamental EMF in each phase. First we draw. That is displaced by how much angle? 120 degrees. And if you take the sum of these three, EA1 plus EB1 plus EC1, the sum equal to 0. Fundamental three-phase system, the sum of voltages and currents always 0 only. If you add these three, you will get 0. Next, similarly, you try to draw for third harmonics, this one, this one, this one. Okay, first complete up to this. Complete up to this. Third harmonics. Yes, if a source is ungrounded, EMF is peaky only. Similarly, you draw the third harmonic. Third harmonic, let us take third harmonics only. This part, E3 sine 3 omega t, E3 sine 3 omega t minus 120, this one. Let's take the three. Third harmonics. Third harmonics. So if you take third harmonics, in A phase, EA3, what is that? E3 sine 3 omega t. And EB3 is what? Similarly, E3 sine 3 into omega t minus 120. Similarly, C phase EC3 equal to E3 sine 3 into omega t minus 240. Okay, then if you little simplify this, let us simplify little. This will be remain same, E3 sine 3 omega t, and this is E3 sine 3 omega t minus, see, 3 into 120, 360 degrees. Now what is 360 degree? 0 degree starting reference. Now again, if you come back to 360 degree means again you got it 0 degree only. So 360 degree is nothing but 0 degree only. First I will write 360 degree. Okay, in place of this 360 you can take 0 degree. Both are same. Both points are same. 360 and 0 both points same. So this is E3 sine 3 omega t finally. Like that, if you find for C phase, E3 sine 3 omega t minus how much it is, 3 into 240, 720 degrees. Now 720, 360 into 2 again, 720. So both are same points. This is also 0 degree only. Therefore, this is also what finally, E3 sine 3 omega t. Now, is there any angle difference between the three phases of third harmonics, EA3, EB3, EC3? No. This is sine 3 omega t. Or if you take it is just like this, E3 at an angle 0 reference. This is also E3 at an angle 0. Same angle, no difference. This is also E3 at an angle 0. That's why if you draw with respect to phasors, how we will get this? Let this is EA3. Let it is EA3. Now where is EB3? Same angle, that is also 0 degree only. Same angle. So EB3 also here itself. EB3 also in phase. Now where is EC3? That is also in phase. All in phase, but I drawn one after other, one below like that. But all are all three are same line only. And this is EC3. All are in phase each other. So this is called the third harmonics are cophasal nature. Cophasal nature. Cophasal means all in phase, same phase. There is no displacement. But how the fundamentals? A phase and B phase lags by 120 and C phase lags A phase by 240. There is some displacement. But third harmonic displacement is what? 0. Hence, these third harmonics we also called zero sequence components. Zero sequence components. Okay. Third harmonics we also call zero sequence components. Now clear why I'm writing previously E3 at an angle 0, E3 at an angle 0. Third harmonics always 0 degrees only. Now if you take the sum of these three, do you get 0? No. All at same instant. The sum is never 0. But fundamental values, if you observe, they are not same value at any instant. Different you get. That's why sum is, if you take the vector addition of the three, you will get 0. Three phase currents or three phase voltages, anything if you add, that will be 0 only. Okay, like that. Fifth harmonics. So let's take one briefly, fifth harmonic also. Fifth harmonics. Fifth harmonics. So in this is fifth harmonic, E5 sine omega t, E5 sine phi into omega t minus 120, and this is in the three phases. Fifth harmonics we are writing again. So in three phases, fifth harmonics. In A phase, what is the fifth harmonic? E5 sine 5 omega t. And fifth harmonic in B phase, E5 sine 5 into omega t minus 120. The fifth harmonic in C phase, E5 sine 5 into omega t minus 240. Okay, now little simplify these values. It will be remain same, E5 sine 5 omega t only, and it is E5 sine 5 omega t minus 600. Okay, 600 degrees, 120 into 5, and this is E5 sine 5 omega t minus, what is 240 into 5? Calculate this. 240 into 5. 1200, 1200 degrees. Now 0, 360-degree point is also 0, 720 also 0. Like that, if you add again, you will get 1080. Okay, then 600, how can we write? 360 plus 240. Can we write 600 as 360 plus 240? 600 only. 360 means 0. Then finally it is what? E5 sine 5 omega t minus 240. 360 is 0. 360 means 0 degrees. In the same way, how can you write 1200? How can we write 1200? Can we write 1080 plus 120? 1080 plus 120, nothing but 1200 only. So we can write this 1200 as 1080 plus 120. 1200 only. 1080 means 0 degree. 0, 360, 720, 1080. All are same. 0 degree only, that is same point. So finally, if it is 0, 120 is left. Then we can write finally it is E5 sine 5 omega t minus 120. Then if you draw the phasor relation, how we get? See, this is E5 at an angle 0. Let, and this is what? E5 at an angle minus 240. And this one, E5 at an angle minus 120. And if you draw the phasor relation, let A phase first. This is EF5 at an angle 0, now it is EF5. Next, where is B phase? E5 minus 240, it is minus 240. So this is EB5, EB5 it is minus 240. Okay. Next, C phase having 120 degrees. So it is E5 at an angle minus 120. This is EC5. Now observe one important here. Previously for fundamental, what is the sequence we got in clockwise direction? Sequence we always observe in clockwise. The sequence is ABC or ACB. Sequence is observed in clockwise. If you observe clockwise, first A phase here, and then B phase, and then C phase. The fundamental sequence is ABC. This is called, generally we call positive sequence. This is we referred as positive sequence components. Okay, fundamental sequence is always positive sequence. Now what we got in the fifth harmonic? First A. After A, what we have? C phase. After that, B phase. So the sequence of this fifth harmonic is ACB. It is opposite to fundamental. Fundamental A, B, C, but it is ACB. So this sequence we call negative sequence. Fifth harmonic components are the negative sequence components. Remember, it will help you again in your power system. But anyhow, fifth harmonic we are not considering in all our discussions. Only fundamental third harmonic. That's it. If you go higher order, the magnitude of harmonic will reduce. Yesterday I given that waveform also, harmonic magnitude will reduce. So that effect is negligible effect. And which effect is more on fundamental? Third harmonic. After fundamental, whatever is there, that is more dominant. That's why we are considering only third harmonic. We don't consider fifth and seventh and all. Okay. Now let's see the second connection, delta connected winding. Star connection we have seen, and there are two cases again, neutral grounded and neutral ungrounded case. Let's see for delta connection, what is the shape of flux and EMF in that. Completed all of you this? Next, second, first one is star connected winding. Next, delta connected. Delta connected winding. Delta connected winding. So I will give some important information. Observe carefully in this. Delta connected winding. Suppose the three phases of transformer ABC are delta connected. Okay. Then check what happened if you give a sinusoidal source to the delta connected winding. Now, how to connect the three phases in delta? Can you join directly? No. Polarity test important for this also. Previously, I said polarity test is mainly for parallel operation. Not only there, if you want to connect, if you want a three-phase transformer which is designing from three single-phase transformer, then polarity test is important. So I will show you here clearly how to connect the three phases in delta. Observe. Let three phases A, B, C. Three phases A, B, C excited from sinusoidal source. Source is same, previous one, whatever we taken. This is just alternator. Supply given from alternator. That's it. Okay. Here neutral is grounded or not, that is not at all required for us because our winding is delta connected. Very important it is delta. See, this is dot. Let A phase, A phase, B phase, C phase. Okay. A, B, C, three phases. Now how to connect this? Let it is dot. Next, this is dot, this is on dot, and here you should have dotted terminal, and this is on dot, and here you should have dotted terminal like this. How to join? Dot means you can let consider, for example, dot is plus, and this is what? Minus. See, minus is connected to plus, again minus is connected to plus, again minus is connected to plus. So you should connect the three phases in delta with additive polarity. Additive means dot connected with undot, again undot connected with dot, again undot connected with dot, and so on. So opposite polarities you need to join. But previously how you join? How you join? We have joined similar polarities as a neutral point. Similar. Either you can join dotted terminal, that is, or undotted terminal, that is. But here we are joining additive polarity. Additive. I will show you what is the problem if you by mistake not connected. Suppose any one phase wrongly connected. What happened? I will show you. Okay, first listen up to that. Now delta connected winding supplied from alternating voltage source. Then what is the current drawn by winding? When you give a source, it will draw a current. What is that current? Magnetizing current to create flux. In all, magnetizing current will be there. Okay. Now whenever in delta we have particularly phase current, line current concept. In delta, phase current is different, line current is different. But in star, what is the phase current, line current? Same. Phase current, line current is same. Now observe here carefully. Observe carefully. If current is sinusoidal from the source, then what is the flux produced? Flat top. If current is sine, flux is what? Flat top, means phi 1 plus phi 3. Both are there. Then what is EMF induced in each phase? The EMF induced in each phase is E1 plus E3. E1 plus E3. Fundamental plus third harmonic. So in A phase, we have E1 at an angle 0 plus E0. And B phase also E1 at an angle minus 120 plus E3 at an angle 0. And C phase similarly E1 at an angle minus 240 plus E3 at an angle 0. So each phase having fundamental EMF, third harmonic EMF, same as it is in star also. But now what happened? Check. What happened here is plus connected with minus, and so on. Okay, all additive polarity. Now, what happened if you add all these three voltages, that is in three phases, if you add fundamentals and if you add third harmonic, suppose additive polarity, now it is additive. E1 at an angle 0 plus E1 at an angle minus 120 plus E1 at an angle minus 240. Only fundamentals I taken first. Then try to add this sum. Add this only in complex calculator. It is you can solve, not directly. Add this in the calculator complex mode. What is the sum? You will get 0. The sum you will get 0. Sum of voltages in the closed delta you will get 0. Why we are adding all these voltages? Because additive polarity you connected additive. That's why we are adding. Then what is the sum you got? 0. So is there any problem to winding if you add in additive polarity? Sum 0, then is winding will damage? No. Sum 0, no problem for us. There is no problem for winding. When there is a problem for winding, if voltages are very high in that addition. But here sum is 0, so no problem. Insulations will not damage. In the same way, try to add third harmonic in all the three. A phase E3 at an angle 0, E3 at an angle 0, E3 at an angle 0. Now, if you add these three, what is the sum? Is it 0? All in phase, directly 3, 3 it is. So, in that closed delta, the sum of these third harmonics are not 0. What is the sum of the third harmonics? 3, 3. So, when there is a current, when there is a EMF, current will flow or not in the closed delta? There is a path for current through this delta. So, a current I3 will circulate now within the three phases. This is the current I3. How to find that I3? I3 equal to total EMF in the closed delta is 3E3 we got, divided by A phase will offer impedance Z3. Every phase will have some impedance to the current flow, that is Z3. Similarly, B phase Z3, C phase also having Z3. Third harmonic EMF, third harmonic impedance. When there is a third harmonic current, some impedance offered by each phase. That impedance we taken as Z3. Now, what is the total impedance in this? Z3, Z3, Z3. Total 3Z3. Finally, the third harmonic magnitude is E3 by Z3. Now, there is a third harmonic current. It is circulating within the three phases like this, circulating. Now, tell me what happens due to the third harmonic current. When there is a third harmonic current, it will produce a third harmonic flux or not? Yes, just like our single phase yesterday we have seen. It will produce a third harmonic flux, phi 3. Now, what is the reason for this phi 3? The reason for this phi 3 is this actual main flux. Now, this phi 3 cancel each other. Then under steady state, finally, what is the flux in the core? Only fundamental flux. Then what is the shape of flux? Sinusoidal. And what is shape of EMF? Sinusoidal. Okay. So here no need of that new grounding concept. Only for star it is. But with the delta, we have an advantage. Due to this delta connection, even the EMF induced is peaky wave, automatically it will become again sinusoidal because of third harmonic current can circulate in a closed delta connection. Third harmonic can circulate. Third harmonic current. Now, here one important question. See, what is this current we call here? This is A phase, this is B phase, this is C phase. Three lines A, B, C. These are line. This is called line current here. Now, what is the phase current? This is phase current. This is phase current, and this is line current. Now, line current is sinusoidal, we have seen. Now, this current is going inside the three phases. Same output, that line current, whatever is there here, sinusoidal, we said that is going inside the winding, delta connected winding. Again, additionally, a third harmonic current also flowing. Now, in the winding, there are two currents or not? Yes. Then what is the shape of current in each phase? Shape of current in phase. Shape of phase current. What is the shape of phase current? In the phase, inside the phase means in the winding, each phase A, B, C to take. So there is a third harmonic current, and from the source a current is flowing fundamental. So fundamental is there, third harmonic also there. When both are there, what is the shape of phase current? Peaky wave. The shape of phase current is peaky wave. And what is the shape of line current? Tell me. Shape of line current, if they ask, what is the answer? Line means this is. What is the current going from the source? Only fundamental, sinusoidal. The shape of line current is sinusoidal. Okay, remember this point. So, write two important points below this. So I will tell you, wait, I will tell you what happens if you don't connect this delta connected winding properly. So I will tell you that after these 2 points. Write the 2 points first. Right. In delta connected winding, there is a path for third harmonic current. There is a path for third harmonic current. Third harmonic current in addition to fundamental current. In addition to fundamental current. In addition to fundamental current. Hence, the resultant shape of current is the resultant shape of phase current is peaky wave, comma, due to this the flux and EMF induced. Due to this the flux and EMF induced in the winding. EMF induced in the windings is always sinusoidal. The windings is always sinusoidal. Is always sinusoidal. So no problem for delta. There is no problem for delta. Problem is for star connected winding. When there is a problem, whether neutral grounding or not, you should check. If neutrals are not grounded, there is a problem. Problem for which voltage again, or which loads? Single phase load or three phase load? Problem is for single phase loads, but not three phase. Why three phase? I said line voltage is no problem. Problem is for phase voltage only. But in delta connection, always the EMF induced is sinusoidal only, because there is a path for current, third harmonic current, immediately it will flow. Okay. Yes. I3 is not coming from source. You no need to observe current I3 is coming or flowing in the source or not. We need to observe in our phase winding current I3 flowing or not. That's it. I3 flowing or not in each phase? Yes, flowing. So whenever there is a I3, what is the resultant current in that? Already fundamental current is coming from the source and third harmonic circulating there only. Then what is the resultant current in the phase? Peaky wave. So flux will become sinusoidal, EMF also sinusoidal. For delta, you cannot connect single phase loads. Delta not suitable for single phase load. Delta is not suitable for single phase load because is there any neutral point in delta? No. Then how can you connect single phase load? Delta for only three phase loads. Okay. Now let's observe here what happened by mistake if you connect delta wrongly. So this is one of the question in our material also. See that. By mistake, one of the phase wrongly connected in delta. Check what happened. Let it is A phase, B phase, C phase. So while connecting these three phases, A, B, C, by mistake wrongly connected. Check what happens now. Suppose A phase, let this is dot, this is on dot, and here we have to connect dot. Okay, but by mistake I placed dot here, one phase only. So actual dot, so I will take first correctly. This is dot and this is dot and this is dot. This is our exact connection, okay, of delta. Dot connected, see, dot connected with undot, dot connected with undot, dot connected with undot. This is additive polarity. This is our correct connection. But by mistake, one of the phase winding wrongly connected. So which phase you want? Take any phase, A, B, C, anything, any one phase you can consider. Any phase. Let's take any one phase. So by mistake, suppose B phase wrongly connected. How? Actually dot is here, but this is placed here. By mistake it is. Now what happened? First, before that, observe. Whenever it is properly connected, this is E1 at an angle 0. This is E1 at an angle minus 120. This is E1 at an angle minus 240. So only fundamentals I am showing. Only fundamentals. Now observe what is the sum here. How we write sum? No, additive. Additive it is E1 at an angle 0 plus E1 at an angle minus 120 plus E1 at an angle minus 240. Then if you add these three, we are getting 0. This is actually, but by mistake, one of the phase winding wrongly connected. Now I will take B phase is wrongly connected. See, dot is placed here. By mistake, one phase wrongly connected. Now check what is the sum of voltages here. This is this will damage complete transformer winding. See what happened. See, first A phase, E1 at an angle 0. Then observe dot is connected with dot. So additive or subtractive? Subtractive. So minus E1 at an angle minus 120. EMF magnitude is same, but because of polarity changed, you are getting negative here. Next, again undotted. This is also undotted. Minus minus is connected. Subtractive polarity. So minus E1 at an angle minus 240. So all of you add this in your calculator and tell what is the value. So add this. Take E1 outside. 1 at an angle 0 minus 1 at an angle minus 120 minus 1 at an angle minus 240. Tell what is this sum? All of you should add this. Yes. This is 2E1. 2E1 it is, right. 2E1. The magnitude is 2. You will get 2 it is. The magnitude you will get 2E1. Okay. This is what? The sum around, sum in delta. Sum in delta. If you add, you are getting 2E1. But previously, what is the sum of these three voltages? 0. But now sum is not 0. Sum is double the rated voltage. Suppose if you take E1 is the rated EMF in each phase, 2E1 is double the voltages. Now, as voltage is 2E1, a current will flow or not? Previously, voltage is 0, sum 0. So, no current, no fundamental current in that. But whenever there is some voltage, what is the current flowing? A current will circulate in delta called additional circulating current 2E1 divided by impedance of A phase Z1 plus impedance of B phase Z1 plus impedance of C phase Z1. Then what is this? A very high circulating current or not? Yes. Impedances are very small, but voltage is double 2E1. So very high circulating current will flow in delta. Very high circulating current will flow in delta. Now it will damage the insulation of the three phase windings or not? Yes. But previously voltage 0. So is there any circulating current? No circulating current. there is no circulating current, windings will not damage. But due to this wrongly connected, by mistake wrongly connected, the high circulating current is flowing through the three phases, which will damage the windings. Okay, so by mistake also we should not connect wrongly. Yes, Jitender. So under steady state, EMF is sinusoidal. EMF is sinusoidal, I said. Then you are considering that E3 will not be present. Yes, E3 will not be present. Then I3 also zero. Then I3 cannot circulate. How again current is peaking? That is your doubt. Okay. So here, this is a continuous phenomenon. Means, see, first initially when you use source, current is sinusoidal. Then initial flux produce flat top, phi 1 plus phi 3. Then EMF induced is peaky wave, E1 plus E3. Now due to that third harmonic EMF, we are getting a third harmonic current. Due to that I3, the resultant current become peaky. Then once current is peaky, we are considering flux is sinusoidal, EMF is sinusoidal. Means this is not end here. You let us think in other way like this. See, E1, E3. Due to E3, a current I3 is flowing. Okay. Due to that I3, a flux phi 3 is produced. Now this phi 3 is cancelling out the actual flux phi 3. Now both getting cancelled continuously. Both getting cancelling continuously. So this phenomenon continuously takes place. So under steady state, phi 3 cancelled out in the core. Which flux is only present in the core? Phi 1 only present. Okay. So don't think like once it is a peaky wave, flux is sinusoidal. Flux sinusoidal means phi 1 only there. Then if there is only flux sinusoidal, EMF also sinusoidal, then E3 0, I3 0. So not like this. This is a continuous phenomenon from now. This phi 3 continuously trying to cancel each other continuously. That's why flux is only sinusoidal fundamental, because phi 3 cancel. Like that we have to consider. Okay. Um, C dot placed correct only. Okay, observe. C dot correct only. So I changed only B phase. When you change only B phase, then you come in one loop here, one direction. Oh, this is dot dot subtractive now. Again undot undot. Anyhow C correct, but undot undot subtractive you are getting. That's why I taken minus. Okay. B winding reverse, then only B phase voltage we should not take. You should take C phase also. Why C phase? You are getting subtractive polarity, na there. Jadhav, you are getting doubt. Why are we studying this phenomena? What are its disadvantages? So here the topic is, that is point is not related to advantage or disadvantage. We should know what is happening in that first. What is happening in star connection, delta connection due to this non-linearity operation. So for that, to know that, we are studying all this. Okay. So generally I will also get one doubt. Who is better? An electrician is better, an electrical engineer is better. Who is best? An electrical engineer or electrician? Tell me. Don't say electrician because we are engineers. Always engineer is the best. Without engineer, is there electrician? Maybe you can consider that electrician, they know everything well. They know practically well, but they don't know what is current first, what is power, what is energy, why we are calculating, what is the use of all this, and how much conductor to be used. Everything we will design there, but we don't know all this first. That's why we feel that they are best. Now, suppose there is a ceiling fan. That fellow know everything to fix and to open, to repair, to place the winding, everything they know, but they don't know the actual how it is operating, how it is operating. Why there are two windings in that, main winding, auxiliary winding? Why there is a capacitor in that? They know practically everything. So if you remove capacitor, fan cannot rotate. They know, but what is the reason behind this? They don't know anything. And they can fix switches and everything, okay. But can you fix a switch? Can we fix a switch directly? No, we don't know, because their job is different, our job is different. Ultimately, engineer is the best, but don't say electricians. But they have practical knowledge, but not theoretical knowledge. But we have very well theoretical knowledge, but not practical knowledge. So once you little build your practical knowledge, you are the king. Yes, good. Electrician or junior engineers. Yes. Negative sequence also will be there, but higher order, no, we are neglecting. We are not considering all this. Only fundamental third harmonic we are considering. And Mohammed, what is mistake in the loop KVL? So when you do with the right one, this is sum addition. We are getting additive polarity. And when B phase is reversed, dot polarity is changed, then we are getting this. Okay, whatever that may be from plus to minus or minus to plus, you are moving. Anyhow, you will get same magnitude 2 even. No, check it is. Whatever the angle, so magnitude only I'm asking, 2 even magnitude you will get. Okay. These are all theoretical questions only. Mathematically, numerical models are very less on this. Only in three-phase transformers you will get numericals again. So here totally theoretical questions. Okay. So this is about star and delta connected winding. So if there is a delta connected winding in transformer, there is no problem at all. So we have four connections now total. What are that? Delta delta, delta star, star delta, star star. Total four connections we have. Now, one more important point you should remember is either on primary or on secondary. Any one side, you must have delta connected winding in a transformer. If there is a delta connected winding either on primary or on secondary, any one side, the shape of EMF in the transformer always sinusoidal. So remember blindly this. But in which connection there is no delta first? There is no delta means star star. There is no delta. Primary side also we don't have. Secondary side also we don't have. So star star connection. With star star connection only, we have the problem of EMF, sinusoidal or non-sinusoidal. And remaining all delta delta, delta star, star delta. The EMF is always sinusoidal. There must be a delta which provide a path for third harmonic current. Any side, primary side or secondary side, any side that is, you must have delta. Okay, make a note of this point. Note. So write your one, it is, write the point. In three-phase transformers, in three-phase transformers. There must be a path for third harmonic current. There must be a path. There must be a path for third harmonic current. There must be a path for third harmonic current within the three phases. Within the three phases, either on primary, or on secondary, either on primary or on secondary. Then the shape of EMF induced, then the shape of EMF induced in the winding, the shape of EMF induced in the winding is always sinusoidal. The shape of EMF induced in the windings is always sinusoidal. Yes, actually there is a chance this year to release Transco Genco state electricity, but due to this corona pandemic right now, they are not showing any interest to release right now. Actually, it is there, recruitment is there. See, secondary delta will not make IMU peaky wave. It will not make IMU peaky wave. It will make EMF sinusoidal anyhow. So how it is? See, if it is a star delta transformer, if it is a star delta transformer, okay, primary star, secondary delta, and primary star is supplied from what? Source, alternating voltage source. Primary star is supplied from alternating voltage source. What is the current at the primary now? Sinusoidal only. Current is sinusoidal. Whether it is neutral, not grounded, suppose. Sinusoidal. Then what is EMF induced in both primary and secondary? What is EMF induced? E1 plus E3, peaky wave, no? If I mu is sinusoidal, flux is flat top, EMF is peaky. Now secondary side we have both EMF, fundamental and third harmonic. Now what happened internally? When there is a third harmonic, I3 will circulate. Whenever there is I3, it will cause a flux phi 3. Now this phi 3 will, what is the reason for this E3 here? Flux in the core phi 3. And this phi 3 producing E3, this E3 causing a current I3, this I3 again producing phi 3. Now this phi 3 cancel each other within the core. Within the core they cancel. Then is the flux phi 3 present in the core? No. So finally what is the flux again in that? Only fundamental. Like that it will make EMF sinusoidal wherever it is. Okay. Yes, both side delta also we have. Clear, Gopal Krishna? So wait, don't, Jadhav, you are too fast. Grounded, star grounded on both sides. Yes, sir. If you provide a star grounded on both the sides, the EMF will be sinusoidal, no problem. So clearly, I will show you that is in the next coming topics. So okay, up to here, what you need to remember is regarding star and delta. In delta, what is EMF induced? Always sinusoidal. And in star connection, what is EMF induced? It depends on neutral grounding. If neutral grounded, what is the shape of EMF induced? Sinusoidal. And what is the line voltage always there? Sinusoidal only. Suppose if neutral is not grounded, then what is the shape of EMF induced? PQ. Okay. So remember these points enough up to this. This is the effect of non-linearity in three-phase transformers. So let's see some numericals questions. See this question. See the question. In which one of the following sets of three-phase transformer connections will zero sequence current be present in the transformer winding? Zero sequence currents means what? Third harmonic currents. So where third harmonic currents will be there? On primary and secondary side, they asked three-phase transformer connections. First option is primary in star neutral grounded, secondary in star neutral ungrounded. Second option, primary in star neutral grounded, secondary in delta. Third option is primary in star neutral non grounded, secondary in star neutral grounded. Next, D, primary in star neutral not grounded, secondary in delta. In which of the following sets, means primary and secondary, both primary secondary of three-phase transformer connections, will zero sequence currents be present in the winding? Primary side, secondary side, both sides they are asking three-phase third harmonic current. So what is the answer? Yes, directly visible. So in star, when there is a third harmonic current, when neutral grounded. In delta, always we have third harmonic current, no doubt. Then only one option is there. Yes, yes, right. All of you correct. Option is D. D is right. Primary star neutral grounded, so third harmonic current path is there, and delta always provides a path for third harmonic current within delta. Okay, this is correct. Next question. Next question. See this. Okay, before that, see this question. See this question first. Question is very big. Question is very big, but already we know about this. Already, just now we have seen this question. What is the answer? Primary delta here and star here. Secondary delta here, star here. First read the question. A normal two winding three phase delta delta transformer connection together. See, this is primary, this is secondary. Primary delta, secondary also delta it is. Okay, corresponding phasor diagram they given. Corresponding phasor representation. Primary side phasors, secondary side phasors. Delta delta transformer only it is. Primary delta, secondary delta. Now read question. A normal two winding three phase delta delta transformer connection together with corresponding primary and secondary phasor diagrams as shown above. The magnitude of each of the symmetrical secondary voltages. Secondary voltages are what? This VAB, small VAB. How much it is? E. This is E. This is also E. This is also E. Same voltage. If terminals, see, if while connecting secondary side, means this secondary delta, if while connecting the secondary side, the terminals X1 and X2 of transformer 2. So there are three transformer here. Observe 1, 2, 3 they given. Like ABC we taken. 1, 2, 3. If the terminals X1, X2 of transformer 2 are interchanged by mistake, the resultant voltage around the secondary delta. Just now we have seen. What is the answer? One of the phase by mistake reverse. Terminals of one of the transformer by mistake reverse. Then what is the voltage? Yes, just now we have seen that, but they given it is like big question. Just in delta connection, one of the phase winding by mistake is reversed. Yes, good. Answer is 2. See, transformer A, let transformer B, transformer C. What is they are asking? The transformer B, secondary side transformer B winding by mistake interchange. If you interchange, what is the resultant voltage around the closed delta? 2E. Okay, just now we have seen. So directly you can refer that question. Just now I have given here this one. If any one phase by mistake reversed, what is the voltage around closed delta? This 2E. This is. If you properly connect, what is the resultant voltage around closed delta? 0. Suppose if you get same question in a delta properly connected, what is the resultant voltage around closed delta? Answer is 0. But by mistake, any one phase reversed. Then this is the answer 2E. Okay. If two phases are changed, you try to write the equation and check what is the answer. Serious question first. Serious question. A 6.6 by zero point 0.4 kV 100 kVA distribution transformer has 1.2% resistance. Percentage R is 1.2% and percentage reactance is 5%. The voltage to be applied to the primary to maintain secondary terminal voltage at 0.4 kV at full load 0.8 leading power factor. Yesterday we solved in the voltage regulation one question model, that is what is the new voltage to be applied in order to maintain same secondary terminal voltage just like E2. E2 is what? 0.4. So secondary terminal voltage should be required 0.4, same voltage without any drop. Generally there is voltage drop, and without that we need to apply some new voltage to the primary side so that the terminal voltage will be 0.4 kV. What is the formula given? The new voltage required is the old voltage V1 plus percentage regulation into V1 or per unit regulation into V1. Per unit regulation into V1. So first calculate per unit regulation is how much? Calculate per unit regulation directly. Percentage or per unit regulation. What is the percentage regulation formula? Percentage or cos phi minus y minus. These are all important. Every time not plus. It is given in the question leading power factor. For leading minus percentage x sin phi. Okay. Calculate this regulation first. R is 1.2, cos phi is 0.8 minus x given 5.6. This is how much? Calculate it is how much? So this is I'm getting minus 2.04 percentage, right? Minus 2.04 percentage negative. 0.8 leading is mostly the regulation will be negative only. Okay, so whatever regulation you got, now use this equation directly. Therefore, the new voltage to be applied is V1. What is the V1 already? 6.6 kV, that is 6.6 kilovolts or 6600 plus what is the regulation we got? Negative. This is in percentage in per unit minus 0.0204 into 6600. This much voltage we need to apply in order to maintain same secondary terminal voltage also. Then you will get less than 6600. You need to reduce the voltage here. No need to increase. Reduce. What is the answer? Oh, answer is yes, 6465 volts, right? 6465 volts. This is the voltage we need to apply. Actually, how much voltage is there? Previous V1 6600 is there. Now, what is the new voltage? Less than 6600. Then how, if you reduce, is it possible? Yes, because the power factor is leading. Leading means what type of load? Capacitive load. So when there is a capacitive load, generally terminal voltages increases. Generally terminal voltage will reduce for lagging power factor or UPF case. But for leading power factor, the terminal voltage generally increases. If zero point 0.4 is the E2, V2 will be greater than 0.4 or zero point 0.4 kV, 400 volts, greater than that. But if you want same 400 volts, you need to reduce the input voltage. So that new voltage is 6465. Okay. So in yesterday's problem, we have increased because lagging power factor is there in that check. Okay. Okay. So before solving that questions, we need to complete some three-phase transformer data. So after completion of some introduction part of three-phase transformer, we will see that numericals. So before that, take a break of 20 minutes and then come back. We will see. So now we will start three-phase transformer after break. So see this question, all of you. Rameshwari, fifth harmonic magnitude is less. That may be negative sequence or negative sequence, and seventh harmonic we call again positive sequence. But anyhow, what is the magnitude of that fifth harmonic compared to third? Small, no? That's why that higher order we neglect. Okay, the effect of that fifth or seventh on fundamental is less. See the question. This is previous gate question. Star delta transformer as shown above is excited on star side, means input is given to star side, supply given. Okay, the transformer is under no load condition. The first question is, second question. First question is, with both S1, S2 open, the core flux waveform will be dash. See, first of all, is there any meaning of S1 in the given question? S1. If you close S1 or if you open S1, is there any closed path we are getting? Neutral is ungrounded case, it is. Neutral is not grounded, just neutral is there. So just to confuse, it is given here as S1. Whether there is S1 open or S1 closed, nothing will change. It remains same only. So with both S1 and S2 open, the core flux waveform will be dash. Shape of flux in the core is dash. Tell what is the answer? Shape of flux. Shape of flux in the core is dash. Okay. Okay, good enough. Yes, the answer for this is flat top. See, whenever S1 open, S2 also open, is there any closed path for third harmonic current? Previously, I given one note point. In a three-phase transformer, we should have a closed path, either on closed path for third harmonic current to flow, either on primary or on secondary. But here, both sides, there is no closed path because S2 also open now. Actually, if delta is there, what is shape of EMF induced? Sinusoidal, because shape of flux will become sinusoidal. But switch open na here, S2 open. Because of this reason, as S2 is open, what is the primary current now? Current drawn from supply is what? Sinusoidal. Flux produced in the core is flat top. So the answer is flat top. Okay. Next, second question. With S2 closed, see S2 closed, S1 open. You forget about S1 first. No use of that S1 open or closed. Just wantedly given. Our observation must be on S2. S2 closed. Yes, delta now. Now this delta will provide a path for third harmonic current. The current waveform in delta winding will be dash. Shape of current in delta winding is dash. What is the answer? Tell me what is the answer? Important it is. Answer. Okay, most of you giving A, some of you given C also. Yes, okay, enough. Now check your answer. The answer for this is only third harmonic. Only third harmonic is the answer. Not sinusoidal. Not sinusoidal. Because in delta, when there is a closed path available for the flow of third harmonic current, what happened now? First of all, one important observation in the question is this. Transformer is under no load operation. This is our important observation. No load means load is not connected on secondary side. If you don't connect any load, is fundamental currents will flow here? Is the fundamental currents will flow? No, it won't flow first. There is no fundamental currents. But As there is a path for third harmonic current is circulating or not? Yes, that is circulating. Whether there is load or no load, third harmonic current depends on what? E3. That's it. So due to that, third harmonic current is circulating continuously. But as there is no load case, what is the current I1? Fundamental current? No fundamental current. That's why only third harmonic is flowing. So answer is only third harmonic. Suppose in the same question they given there is a load on transformer. Load is there. Now what is the shape of current in the secondary winding? What is the current waveform in delta winding or secondary winding? When there is a load, fundamental current will flow to the load in the lines, and already there is third harmonic current in the winding inside. Then what is the resultant current? Peak E wave. The resultant current is peak E wave. Okay. See, remember, no load is different, load is different. If there is no load, only third harmonic is the answer. If there is a load, the answer for the the shape of that current in the delta connected winding is both will be there. So when there is both, the current waveform is peaky wave. Okay. See, S1 no use, because this is a star given on primary. Actually neutral is there, but they are keeping again one more switch, but neutral is not grounded. It is not given now. Neutral is ungrounded only, and just they given switch. Is there any use if you close and open this switch? If you close, third harmonic will flow, or if you open, third harmonic will flow? No, just wantedly given S1. No use of that S1. That's why I said no need to consider S1. Okay. Clear? Four wire means neutral, that is neutral wire. Wire is there, but neutral is ungrounded. If grounded, then it will be different again. If neutral is grounded, then source neutral also should be grounded. Then shape of current is there itself, peaky wave, and flux produced is sinusoidal, EMF also sinusoidal. Okay. Okay. Next, let's see now. So with this single phase transformers is complete. Now three phase transformers. Three phase transformers. Now, up to now we have seen only single phase. Now three phase from here. Tell me first, what is the need to go to a three phase transformer? Up to now single phase. So these three phase transformers we are using are required for us whenever the load capacities are increasing. Whenever load capacity increases, high capacity like 2 MVA or 1 MVA in MVA, volt, megavolt ampere, are very high power rating applications. Okay, whenever it is required to supply heavy loads, then single phase transformer not suitable. Suitable, but problem is not economical. Single phase transformer also suitable. Suppose a load required a power of 1 MVA, for example, very high, 1 MVA. Then to supply this, what should be the rating of voltage and current? High voltage, high currents required, for example. Now, if you take a single phase transformer, single phase, how many turns required? Very high. And what should be the thickness of that wire? Very high, because high current, high voltage, more turns, more current, more thickness. Then if you design one single phase transformer for this much rating, the transformer cost and size will increases. So it is not finally economical. It is not economical to design a single large transformer, single phase large transformer. So in place of that single phase large transformer, we will design directly a three phase transformer. So if you design a three phase transformer in order to supply that high capacity loads, your size and cost of transformer will reduce, So totally it is a economical. This is economical. So three-phase transformers are economical to supply a large capacity loads, but not single phase transformer. Okay, anyhow, how to design a three-phase transformer? Then how can we get a three-phase transformer? Yes, we can get a three-phase transformer in two methods. One is, now already what we have, single phase transformers we have. Now let us take three single phase transformers and connect the three single phase transformers as a one three phase transformer. Connect it as a three phase transformer and supply to load. That is one method. And other method is design directly a single three phase transformer using separate magnetic core. Design directly a single three phase transformer. Two ways we can design a three phase transformer. One is by using three single phase transformers, and second is directly designing a single three phase transformer. Okay, now two we have. So let's see what are the differences in these two. Which one is best? Both are required. Both are required, but which one is best for most of the applications? So let's see that right here. Difference between a three phase transformer bank, a three phase transformer bank, and a single three phase transformer. A single three phase transformer. First, write this. I will tell what is the three phase transformer bank and single three phase transformer. So, three phase transformer bank is nothing but I said first method is what? Designing a three phase transformer using three single phase transformers. Commonly, we call that is a three phase transformer bank and single three phase transformer. Single transformer only, that is a three phase transformer with single unit. And here we have three single phase transformers combining as a three phase transformer. So let's see the figures. Side by side, right? It is three phase transformer bank and single three phase transformer. Single three phase transformer. Take the figures first. Three phase transformer bank means we are considering three single phase transformers like this. Let transformer A primary, secondary. Okay, one single phase transformer. Take three identical, same only, because in all three phases same voltage we need to apply. So A phase primary, secondary, B phase primary, secondary. This is one transformer. This is other transformer, and one more C phase primary, secondary. Okay, three single phase transformers taken. A, B, C. Let this transformer A let it is transformer A, transformer B, primary, secondary, transformer C, primary, secondary. Okay, secondary side small a, small b, small c. So before connecting it is as a three phase transformer, what we have to do? Polarity test, because three phase means you need to connect in delta or star. Okay, so anyone. So I'm considering for simplicity star connection. So dot is here, dot is here, dot is here. Now how to connect in star? Star, connect the three phases with the same polarities. Connect three terminals with the same polarities from three phases like this. This is undotted terminal. I'm connecting to this undotted terminal and connecting to this undotted terminal. So this is a star connection. So here we give supply A, B, C, three phases. This is one phase, B phase, C phase. Star connection it is. Similarly on secondary side, dot polarities are marked and connect same polarities A is joined undotted, 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 undotted. So this is our star star transformer. Star star taken for simplicity. You can do delta or star anything. Okay. A phase, B phase, C phase. This is three-phase transformer bank we call. Designing a three-phase transformer from three single-phase transformer. Now let's see what is single three-phase transformer means. In single three-phase transformer, we have same core. Core is same, but observe here three different cores we have A, B, C. But here same core it is. On the same core we place winding. Let this is A phase winding. This is B phase winding. On the same core, we are placing the three phases A, B, C. Okay, three phases A, B, C. So let us assign the names A, B, C. Now again connect. This is also star star. I am taking. Okay, primary star, secondary star is taken in both the cases. Now what is one important difference from between these two? Designing of three-phase transformer using three single-phase transformers, designing directly a single three-phase transformer, single unit of three-phase transformer. Now, what is one main difference between these two? In the first case, in the three-phase transformer bank, observe in three-phase transformer bank, the three phases are electrically connected, but magnetically isolated or not? Yes. How? These are three single phases. Transformer A, this is primary, secondary. Transformer B, primary, secondary. Transformer C, primary, secondary. So individually, we are joining just wires, we are joining. That's it, like this. But magnetic circuits are different for each one. A phase different, B phase different, C phase different. Means core is different for three phases. But in the second one, what is the core for three phases? Same. So here the three phases are electrically connected, magnetically also connected. But in the first one, the three phases are electrically connected, but magnetically isolated. Magnetically A phase different, B phase different, C phase different. Okay, so write the first point. Take the figures first. Taken. Right. First point. First point. In this, the three phases are electrically connected. The three phases are electrically connected, but magnetically isolated. But magnetically isolated. Magnetically isolated. Next, first point in this. And in the second case, what is the three phases? Electrical connection is there, and magnetically they are coupled. Magnetically also connected. So right there. In this, the three phases are both electrically and magnetically coupled, magnetically connected, magnetically connected. So both are there in this. Okay, next, second point. Observe second point. Tell any other important differences in these two. Any other? Just by looking diagram, you can guess. In the first case, three individual single phase transformers. This is separate iron. This is separate iron. This is separate iron. Then what is the overall space it is occupying? More iron, more space. But here in second case, only single iron. Then what is the space required for this? And what is the size of the transformer also? Reduced. So first one required more space and second one less space because of iron is less mainly. And here more iron, three different cores. Write that point. Second point. It requires more space, more space due to three different transformer cores. Three different transformer core. Second here the space required is less because only one core will be there, overall core. So space or iron required is less, so space required also less. Right? It requires less space. It requires less space due to single core of transformer. Single core of transformer. Okay, single core of transformer, space required is less. Next, third point. Observe any other important difference. And if you talk about maintenance here first, maintenance, see, transformer A, this is transformer A, transformer B, transformer C. This transformer having two terminals LV, two terminals HV. Let us consider LV primary, HV secondary side. B also having two terminals primary, secondary, and C also primary, secondary. So total, how many LV terminals you are getting in this case? 6. And total, how many HV terminals you are getting in this case? 6. So whenever there are more terminals, means each transformer having two terminals primary, two terminals secondary, then total how many bushings required? Bushing. Why bushing? The terminals of transformer we will take outside through bushings only, insulators. Now LV 6 LV bushings and 6 HV bushings. Total 12 bushings required in this case. But how many bushings required in the second case? 3 terminals primary, 3 terminals secondary. So only 6 bushings, so overall 6 bushings. So no need of 12 number of bushings. Then what is the size and cost of these bushings? Reduces. So we no need to take 12 bushings here, only 6 bushing. Cost reduce, maintenance also reduce. Okay, so write that point. First, it requires more number of bushings. It requires more number of bushings. And transformer tank increases. So 3 single phase transformer, 3 tanks will be there, and 3 different oils will be there in that. So everything is different. So overall cost is what? Increases. It requires more number of bushings, comma, cost increases, comma, size also increases. Okay, cost increase, size increase. But in the second case, only 6 bushings, 3 LV, 3 HV. So if you take neutral also outside, 4, that is a 4 LV, 4 HV. So less number of bushings are required. It requires less number of bushings. Less number of bushings, comma, size reduces, cost reduces. Okay, size also reduce, cost also reduce. For second one. Next. Completed. Next point. Now whenever there is more iron material, iron loss also increase or not? Yes. So as it is having more iron loss increases, but here iron is less, so iron loss little reduces. And the main one more advantage of this three-phase transformer bank. So there is some advantage also in the first one. What is that advantage? See here now. Suppose if any one phase fault takes place, generally ABC three phases we have. Generally in any one of the phase sometime fault occur. Fault means some short circuit takes place in one of the phase winding. That winding gets open. Then we need to replace that only faulty phase or not? Yes, we need to replace. Now in which case you can replace the faulty phase easily? First one or second one? Yes, first one we can replace easily the faulty phase winding, but not second. Why? These three single phase transformers are individual outside. Suppose B phase transformer, B phase winding gets damaged. Now remove that second transformer, B phase here, and just remove that outside from the electrical connection and change the winding easily and then replace. So easily you can replace if any fault takes place in one of the phase. Suppose there is a fault in second case. In one of the phase A, B, C, in transformer or phase B, fault takes place. Can you replace easily? Can you replace easily? Don't say that yes, you can replace. Yes, we can replace. No, no doubt. But can you replace easily? No. Why? Because if you want to replace, you need to open the complete tank of the transformer first. That is, you need to take that core winding outside. At that time, you should disconnect completely the transformer from the loads. You should take the transformer outside first without any supplying. But in the previous case, even one phase is damaged or fault takes place. With the remaining two phases, you can give continuity of supply to the load. That connection we call open delta connection. That is called open delta connection. So we have one of the special connection in the transformers, that is open delta connection. So open delta connection is possible for three-phase transformer bank, but not a single three-phase transformer case. Because in three-phase transformer bank, A phase magnetic circuit different, B phase is different, C phase is different. If any one phase is problem, it won't affect the magnetic circuit of other two phases. They are individual. But in the second case, check here. If any one phase is gets problem, what is the magnetic circuit for all the three phases? Same. So if one phase is problem, the flux created due to B phase will affect the remaining two phases. Because suppose B phase, A phase, B phase, C phase working properly, there is some flux produced by each phase. Suddenly one of the phase, B phase winding fault or open. Now, is there any flux produced by B phase winding? No. Then that flux will affect the remaining two fields or not? Yes, because they are on the same core, same magnetic material. So due to this reason, open delta connection is possible for first one only, not for second case. Okay, so write that point. Fourth point. Four. If any fault occurs, if any fault takes place in one of the phase winding, in one of the phase, it can be replaced. It can be replaced easily. It can be replaced easily. If any fault takes place in one of the phase, just remove that corresponding single phase transformer and replace easily there. Okay, but in second case, easily you cannot replace. Complete transformer you have to open. Okay, that is difficult for us right here. If fault occurs, if fault occurs in one of the phase, in one of the phase, then it is difficult, to replace the faulty phase. It is difficult to replace the faulty phase. Okay, next, fifth point. Fifth. Now tell about spare transformer. Spare spare transformers. What is the need of spare transformer? Spare transformer purpose is what? Spare. Why we keep spare or standby or stepney, we call simply for four wheelers. Generally we keep stepney, or in any transformer substation if you visit, in some substations we have standby transformers are called spare transformer. What is the need of that spare? Because there are three single phase transformers working, supplying some load. One of the transformer fault occurred, then can you replace immediately that winding? No, immediately you cannot repair. It will take some time, maybe 3 hours or 4 hours or one day also. So up to that, there will be some disconnection of load. So to maintain continuity to the load, we need a spare transformer readily. If a fault occur, remove that faulty transformer and replace the spare transformer. Then spare transformer cost in first and second. Just compare now. In the first case, there are three individual single phase transformer. Suppose transformer A, in this phase A transformer fault takes place. Then what is the spare required? One more single phase transformer, you need spare just. Now whenever fault occur, replace here. What is the cost and size of that small one? Only single phase transformer. But in the second case, if fault occurred in any one of the phase, it is very difficult to replace immediately. It will take so much time than first one. Then in order to continuity of supply, to make continuity of supply, we need a spare transformer. Now, what is the size and cost of that spare transformer? Very high. Why? Very big three-phase transformer you need to keep as a spare. Size increases, cost of that three-phase transformer also increases. So that is the drawback of second one, but advantage in first one. Okay, write that point. Spare transformer. The size and cost of spare transformer is less. Spare transformer is less. Okay, next, fifth one here. But in the second one, the spare transformer size increase, cost increase, because single unit, that is single unit. So the size and cost of the size and cost of spare transformer increases. Spare transformer increases. Okay, but anyhow, finally, which one is the preferred one? First one or second one? Practically, second one only we are preferring, because fault taking place, these are all not regularly. Every day will not take place fault. That depends on load. But mostly, if you observe in your street also, is the transformer getting regularly daily fault? Daily you are getting power loss? Don't tell you somebody may got. Maybe that is you depends on your area. Okay, but regularly if you take in normal, in an average areas also, fault will not take place daily. It may be for 1 week or 10 days or 1 month or more than that also. So fault is not regularly taking place. That is not important criteria for us to select. Important criteria is initial cost and maintenance, cost and size. Size is very important. So there is a three-phase transformer in your street, single. If you want a bank, a three-phase transformer bank, if you want to replace, how much space it will occupy there? So streets itself very small. Then if they are placing three single phase transformers side by side, so it is very difficult now in some of the areas. Okay, so we need to select based on size and cost of transformers mainly. Now which size and cost of transformer is less? Second one. That's why we prefer second one also, always right here. The size and cost is more, and here the size and cost is less. Size and cost is less because no need of three different iron, only one iron, only one tank. Oil also required is less, but in the first one three different, so size increase, cost increase, maintenance also increase. So due to this reason we always preferred a single unit of three-phase transformer. 90% we use single unit of three-phase transformer, but not single three but not three single phase transformers. This is also called transformer bank. Transformer bank means, remember, three single phase transformers converting as a three phase transformer. Okay. Now make a note. Note. Right. First point. In case of three phase transformer bank, in case of three phase transformer bank, in case of three phase transformer bank, if one of the phase, if one of the phase gets fault, one of the phase gets fault, comma, still it is suitable, still it is suitable to supply, to supply continuity to the loads, to supply continuity to the loads, to the loads by using open delta connection, by using open delta connection, by using open delta connection. Okay, still you can supply. Suppose there is a single unit of three phase transformer, one of the phase fault. Now can you supply open delta there? No, not possible, because magnetic circuit is same for three phases. Then unbalancing will come, it won't work. Okay, then only this three phase transformer bank suitable, because magnetic circuits are individual for this. No problem. If one phase also, one transformer also, if you remove single phase transformer, still you can use supply to the loads. Okay, next, second point. Now we said, just now we have seen most of the cases we preferred second one only. Single three phase transformer we preferred because size is less, cost is less. Single three phase transformer. But in some of the cases, in some applications, the first one only suitable. Can you tell where the first one only suitable but not second one? Tell some applications where three phase transformer bank only suitable but not a single three phase transformer. Where is that? If you know, try to tell. Yes, good. Rural areas, villages, hilly areas, right? Good. In some of the areas, yes, in some of the areas, wherever it is difficult to carry a single unit of three phase transformer, there three phase transformer bank only suitable. Why? Three phase transformer bank having three single phase transformers, one, two, three. Three single phase. This is one phase, this is one phase, this is one phase. But if we take single three phase, very big, no, it is. Single unit is very big. But here, small, three single phase transformers. In some of the areas like hill areas, hill areas means the transportation facility will not be good there. Then how can you carry the large size single three phase transformer? Difficult to carry there, because if road facility is not good. Then single phase transformer means small one, easily you can carry three single phase transformers. So there this is only suitable. Now they will carry three single phase transformers to the top of the hill. For example, if any supply required there, then they will connect, after taking to there, they will connect in three phase, either delta or star. Then they will give supply to the loads, like that. Hill areas and some rural areas, wherever low voltage supply is required, they will carry this. And one more is in the mines, very important, mines, in underground mines. Definitely road facility will not be there, very, very less in this type of mines. Then can anybody carry a large three-phase transformer, single unit? No, difficult. At that time, they will carry small three single-phase transformers, and they again operate it as a three-phase transformer, and they will give supply to loads. Like that, in some of the areas or applications, the three-phase transformer bank only suitable. Okay. Yes, good. It's one of them. That is also right. So wherever faults mostly taking place, faults, there also single phase is best because easily you can replace. Good one. Islands also good. Yes, hospital for emergency. Okay, good. Anywhere, wherever it is. Yes. In these hilly areas and all, Charan, number of turns may increase with the three different individual single phase transformers. But anyhow, what is important there? Cost important at that areas. Cost is not important. Maintenance important. For that, they will take like this one. Don't think very much. Okay, enough. So this is about the three-phase transformer design using two types, using three single-phase transformer and directly a single three-phase transformer. Okay, let's see now the types of magnetic circuits of three-phase transformer. Right, starting types of three-phase magnetic circuits. Three-phase magnetic circuits. What are the magnetic circuit in single phase transformer? Two types. What are the two? Shell type and core type. Core type transformer we call and shell type transformer we call. Magnetic circuit nothing but core only. Two types we have. Same as it is here also we have two types. Core type and shell type. But we call it is particularly write that. Right side by side the names. Three limb core type transformer. Three limb core type transformer we call. Core type shell type only. Core type shell type only. But we call three limb core type here. And one more is five limb shell type transformer. Five limb shell type transformer. Now, take the figures. Core type transformer. Take the figure. Okay, this is core type. Three limbs here. Core type, three limbs. Generally in core type, where winding is located? Outside or inside? Outside. So winding is located outside, core will be inside. But in shell type, where winding? Inside. Core will come outside. Okay, same as it is here also, but number of limbs increase because phases increases. It is not only one phase. As phases increases, limbs also increases. That's why here five limb shell we call. Five limb shell type. Okay, five limbs will be there here. And in shell type always in the inner limbs winding is located. In core type always in all the limbs winding is located. Now observe the figures. Core type, the winding is located in all the limbs. Three phases. Let this is primary. A phase primary, and secondary. Phase A, primary winding, secondary winding. This is primary, secondary. For phase A it is. Like phase B on this limb. Primary winding of phase B, secondary winding of phase B. Phase B, primary, secondary. Similarly, phase C, primary, secondary. Okay. In core type. Next, in shell type, 5-limb shell type, observe. The winding is always in the inner limbs. So here, this is A phase, primary, secondary. B phase, primary. See, remember, like this, we don't place practically. Just I'm drawing here one phase winding on one limb. How we place winding? Tell me if you remember. Any one winding we place. Which winding we place always first? LV winding first on the limb. Then on that HV winding we place. Not one is top, one is bottom. Just representing both will be there on same limb. Primary of C phase, secondary of C phase. Okay. So 3 phases are placed. 3 phases. Now you can connect the 3 phases either in primaries you can connect in star or delta. Any connection you can make. The primaries you can do either star or delta, and secondaries of 3 phases you can make either star or delta. So based on the combination, 4 types of connections you get: delta delta, star star, delta star, and star delta. Okay. Now whatever the differences we have seen for single phase transformer, core type and shell type, same valid for here also, valid for 3 phase also, but only one point I am discussing now. Only one point in these two, that is, just today itself, when we started effect of non-linearity in 3 phase transformers, I said it depends on 2 things. One is type of winding, whether star connected or delta connected, and second point is what I said, types of magnetic circuit. Now the effect of non-linearity depends on this type of magnetic circuit. Now let's see in which type of magnetic circuit EMF is always sinusoidal. Okay. Now first of all, with respect to winding, which connection we are getting problem? We have 4 connections: delta delta, delta star, star delta, star star. Now in which connection the shape of EMF is non-sinusoidal? In all these 3 connections we have delta. When there is delta, always sinusoidal EMF, no doubt. But only in star star, there is no path for third harmonic current. You should mention neutral is grounded and all. But if you take only star star without neutral grounding, what is the shape of EMF here? The shape of EMF is non-sinusoidal, that is peaky wave. Okay, shape of EMF is non-sinusoidal. Now this case we are taking and analyzing with respect to magnetic circuit. First thing is based on winding. If there is a delta, whatever the core it is, always sinusoidal EMF. Now problem is for star star. Now let's check for star star in core type transformer and shell type transformer, where we get EMF sinusoidal. Let's see that. Observe here carefully. So I'm considering primary star connected, secondary also star connected. Now when you connect star star, primary star, secondary also star. Now what is the shape of current in the winding? Primary current, sinusoidal, no? Source is sinusoidal, so the current also sinusoidal. First, current I mu is sinusoidal. Whenever current is sinusoidal, what is the flux produced here? What is the flux produced? In all the phases, flux will produce. All the phases, primary side, flux. What is the flux produced? Flat top. Flat top is phi 1 plus phi 3. Listen carefully. If current is sinusoidal, the flux produced in each phase is flat top. Flux produced is flat top. Flat top is harmonics. Phi 1 plus phi 3. Now observe. There is a phi 1 plus phi 3 here also. B phase also. C phase also there is a flux phi 1 plus phi 3. So in all the three phases, fundamental flux, third harmonic flux will produce. Now there is an interesting thing. See, the fundamental flux of A phase, fundamental flux of B phase, fundamental flux of C phase. Phi 1, phi 1, phi 1. These three, suppose the fundamental flux of three fields are coming at one point, and what is the sum of these three fields at this point? 0. 0. That's why return path is not there here. For three-phase magnetic circuit, you don't have return path. But generally, remember, in primary single-phase transformer, primary single-phase transformer case, single-phase transformers, remember, if you give supply to primary, whatever flux produced on primary, it will take a path through secondary like this, closed path. But in three-phase transformers, this current, A phase it is, IA, primary of A phase, primary of B phase, primary of C phase. It is producing a current. So when you give three-phase supply, current will go in all the phases. Now it is producing flat top flux phi 1 plus phi 3, phi 1 plus phi 3, phi 1 plus phi 3. And sum of these three fields at any point in the core is 0. Why 0? They are 120-degree displaced. No. However, previously we said three-phase currents sum is 0 or three-phase voltages sum is 0. Like that, the three-phase flux, the flux produced by three-phase currents also 0. See, phi A at an angle 0 plus phi B phase at an angle minus 120 plus phi C at an angle minus 240. If you want all having same flux, let us consider same flux phi at an angle 0 plus phi at an angle minus 120 plus phi at an angle minus 240. Because all three phases having same turns, same current is flowing, so same flux will produce. Then if you add these three vector addition, you will get 0. So fundamental flux, no problem. Fundamental flux is there in the core flowing. Fundamental flux is there. Now observe about third harmonic flux. Interesting, it is third harmonic flux. Third harmonic flux displaced by how much angle? 0. However, third harmonic current 0-degree displacement we call zero sequence. Third harmonic flux also same. Now phi 3, phi 3, phi 3. A phase, B phase, C phase. In all the three phases, third harmonic flux at a time produces. Then if you bring all at one point, is the sum 0? No. The sum is not at all 0. See, like this. So I will show you separately here. Observe this. So I'm showing only third harmonic flux. This is A phase. I'm not drawing complete winding. In this A phase, the total flux produced is phi 1 plus phi 3. Third harmonic flux, fundamental flux. And here also, both the fields will produce phi 1 plus phi 3. And in this C phase also, flux will produce phi 1 plus phi 3. Okay, phi 1 plus phi 3. Now, phi 1 of A phase, B phase, C phase are balanced each other, three-phase system. But I am considering only phi 3, only phi 3. So this phi 3 will come here, and this phi 3, this is phi 3, and this phi 3. And what is the sum of these three here? 3 phi 3. Phi 3 plus phi 3 plus phi 3. Not 0 it is 3 phi 3. Now, this is total 3 phi 3. Means there is some flux at the sum or this point or not? Yes. Now, it should require a closure path or not? Yes. Now, where is the closure path? How that flux will go now? How that flux will go? Now, this flux, whatever third harmonic flux is flowing, phi 3 plus phi 3 plus phi 3. Now, this flux should take the path through air. Like this, it will complete the path. Through air only, the third harmonic flux has to complete its return path. Why? It cannot flow in the limb. Why? Phi 3 is there here. Now this phi 3 cannot flow like this because already this phi 3 is coming in this direction. They will cancel each other. The only path to flow the third harmonic flux is through air. Now air will offer high reluctance to the third harmonic flux or not? Yes. Third harmonic flux magnitude how much first? Very small. Fundamental is high. Third harmonic very small. And for that small flux, reluctance offered very high due to air gap. So automatically the third harmonic flux will become zero. Automatically the third harmonic flux will become zero in this core type transformer. Whenever phi 3 is automatically becomes zero, which field is there in the core? Only phi 1 is there. Only phi 1. Then what is the shape of only phi 1 means sinusoidal flux. Then what is the EMF finally? Sinusoidal. Therefore, even for star-star connection, whether it is neutral, grounded or not, anything that is, even for star-star, actually with respect to winding point of view, what we said EMF, peaky wave. But if we use star-star connection for core type transformer, the shape of EMF is sinusoidal only. Sinusoidal only. Because just now we have seen the third harmonic flux should complete its path through air, but not through core. But air is offering high reluctance to third harmonic flux. Then automatically it will nullify to zero. Therefore, the shape of flux in the core is only phi 1, that is fundamental, sinusoidal, EMF also sinusoidal. So with core type transformer, there is no problem at all. Whatever the connection you did, the problem is only for star star. For that also there is no problem. Clear all of this? The fundamental flux not cancelling out. Don't think that it is cancelling. Fundamental flux will not cancel. Fundamental flux of A phase will interlink with B phase and also with C phase. They are interlinked and rotate. Inside it is moving. Fundamental flux is there in the core, not zero it is. Okay. Main flux will not become zero. Main flux is there, but only the property we are applying. If you apply the same property for third harmonic, it is not satisfying here. Sum is not zero, then it should complete its path. And where it will complete? Through air only it will complete. But fundamental flux, no need to complete the path. It will be there in the core, but no need to complete the return path. Continuously flux will be there in the core. Okay. So write one point below this. So right below first one, core type transformer. 3-limb core type transformer right below this. Right here. For star-star connection, the shape of current is sinusoidal, comma, which produce a flat top flux, which produce a flat top flux having phi 1 fundamental flux and third harmonic flux phi 3, phi 1 and phi 3. In this core or in this magnetic circuit, there is no path for phi 3. There is no path for phi 3 through the core. Hence it will complete its path through the air, it will complete its path through the air. So next page. Through the air, which offers high reluctance through the air, comma, which offers high reluctance, hence it will become zero, or it will be nullified approximately. It will become zero, then the flux in the core is only fundamental, hence the shape of flux and EMF in the winding is always sinusoidal. Hence the shape of flux and EMF in the winding is always sinusoidal. So even for star winding also, there is no problem for in this type of core or magnetic circuit. So if they say star connection used in core type transformer, what is the shape of EMF induced in transformer? Sinusoidal. Actually, if they say only star winding without any magnetic circuit, so there is a star transformer supplied from sinusoidal voltage source. What is the shape of EMF induced in that? Peaky wave, because there is no third harmonic current on both the sides. When there is no third harmonic current path, definitely EMF is peaky wave only. But in this core type transformer, that is magnetic circuit is core type, even for star, the shape of EMF is what? Sinusoidal only. That is the advantage of core type transformers. Okay. Now let's see in shell type what happened. Now see about shell type transformer, what happened in shell type core. In case of shell type, now same as it is again, let us consider primary star connected, secondary also star connected. Now when you excite the primary side with sinusoidal voltage source, what is the current flowing? Sinusoidal. Then what is the flux produced in this? Flat top. Current is sine, flux produced is flat top. Here also same, phi 1 plus phi 3. Each phase will produce fundamental flux plus third harmonic flux, phi 1 plus phi 3. Both produce same as it is previous. But check now, fundamental flux of A phase will flow in B phase. They are interlinked each other always. A, B, C, the fields are interlinked like this only, they will flow. A, B, C. A flux in A phase, whatever is produced, it will interlink with B and C. And whatever flux is produced, fundamental flux in B phase, it will interlink with A and C. Like that. They will interlink always. But let us check about third harmonic flux. See, this third harmonic flux in A phase, third harmonic flux in B phase, third harmonic flux in C phase at a time will produce. Because what is the displacement? Zero. All will produce at a time. Now they will fetch for return path. Now where is the return path? Observe. Yes. In this shell type, we have two empty limbs we call. Two empty limbs. Empty limbs. No winding on that. Empty limbs we call. Now in this empty limb, fundamental flux will not flow. Fundamental flux will not flow. And only third harmonic flux, phi 3, phi 3, phi 3. If you take phi 3 and this phi 3 and this phi 3, and what is the total sum here at this point? 3 phi 3. Now this out of 3 phi 3, half of the 3 phi 3 will go in this direction and complete its path, and half of the flux will go in this direction. Like this, the phi 3 will complete the path. Okay, so anyhow, whatever third harmonic flux produced in A, B, C, three phases, there is a path to flow the third harmonic flux. But is there any path in first case? No path. All limbs is having third harmonic flux. Then where is the path? But in the shell type, there is some empty limbs. Now there is a path to flow third harmonic flux continuously. Now in the core finally, how many fields are there? Phi 1 is there and phi 3 also there. It is not becoming 0 here like in core type. In shell type there is a path for third harmonic flux through this empty limbs. Due to this reason the flux is there, third harmonic flux also there in this. Then when there is third harmonic flux it will cause EMF E3. Then what is the overall EMF induced in the winding? Peak EV. Okay, so where is the problem for star star? With star star connection only in shell type transformer, what is the shape of EMF induced? Peaky wave. Okay, note down this right in the second case. For star star connection, so all of you clear this point? All of you clear about shell type? Three limb core is best. Why we are using five limb is that is one type of transformer. There is some advantage in that. If you neglect this point, there is some other advantages in shell compared to core. Okay, okay, listen one more time. In shell type transformer, five limb shell type transformer, for star star connection, primary star connected, secondary star connected. Now as it is star connected, what is the current flowing from primary? If you give source, sinusoidal current is sinusoidal. So for sinusoidal current, what is the flux produced? Flat top. So that is phi 1 plus phi 3 in each phase. Now if you consider only third harmonic flux, so any of fundamental flux will be there in the core. We are talking about mainly phi 3 here. If you take phi 3, see third harmonic flux at a time will produce in all the three phases at a time. A phase phi 3, B phase phi 3, C phase phi 3, all are there here. Now they want return path. They want return path. Previously in core type transformer, only three limbs. In all the three, phi 3 is there in same direction, same direction. Now they will oppose each other, they will oppose each other, they cannot complete its path. The only path is air, through air. But air offers high reluctance. So that is zero there. Phi 3 automatically becomes zero. But in shell type, phi 3, phi 3, phi 3. Now total 3 phi 3. Now the third harmonic flux will require return path. Now where is the return path? Through the outer or empty limbs. We have empty limb here in shell type. Now through that empty limb, the third harmonic flux will complete its path. So finally, as there is a path for third harmonic flux, it won't become zero. It is not zero. Therefore, third harmonic flux is there in the core or not? Yes, it is there. Now, what is the overall flux in the core? Fundamental plus third harmonic. Now, what is the shape of flux? Flat top only. Then what is EMF induced in the windings? Peak EV. Okay, right now. Clear? Abhinesh. In single phase transformer, third harmonic flux use which path? So there, third harmonic flux is produced. So clearly that concept is over. No, again we should not go because should not confuse. Okay, you try to go to previous topic, single phase transformer effect, and check there once you will understand. Okay, why third harmonic required empty limb? See, third harmonic required a path, not empty limb. Means the empty limb available for shell type. That's why it is taking that path. If empty limb is not there, then where it will flow? It has to flow in air only. Okay, as it is available, it is flowing in the empty limb. That's it. Yes, low reluctance path, right? Third harmonic flux will take always low reluctance path. No, simple. Clear? Right here for star star connection. the shape of current. The shape of current is sinusoidal, comma, which produce a flat top flux. Which produce a flat top flux. Which produce a flat top flux. In this core, or in this magnetic circuit, flat top flux means fundamental and third harmonic flux both are there. In this magnetic circuit, there is a path for third harmonic flux. There is a path for third harmonic flux through empty limbs. Through empty limbs. Through empty limbs. There is a path for third harmonic flux through the empty limbs. Hence, the resultant flux in the core is the resultant flux in the core. Resultant flux in the core is flat top only, flat top, comma, which produce the EMF in the winding is peaky wave. The EMF in the winding is peaky wave. Clear? So we have the problem of star-star connection. With respect to winding point of view, star-star is having EMF is non-sinusoidal. And we are checking star-star in core type and shell type core. Core type magnetic circuit, shell type magnetic circuit. In the core type, even for star-star, we are having sinusoidal. But only in shell type, the shape of EMF for star-star is non-sinusoidal or peaky wave. Remember this point enough. Okay. Flux in the core. Core means magnetic circuit, not core type, that is. Okay, Vignesh. Flux in the core or iron, simple. Core means don't say core type transform. Yes. So these are the two types of magnetic circuits in three-phase transformers. Core type, shell type, just like single phase transformer. So all of you clear this? So with this operation of non-linearity completed. Operation of non-linearity. Now actual three-phase transformer we will start here. Okay. So today we see some EMF equation related information about three-phase transformer and some small numericals on that. And tomorrow we start actual three-phase transformer connections, because we have some vector groups in three-phase transformer. Different vector groups we have. Vector groups are phasor groups we call. So these vector groups we should know clearly how to find. So particularly already I said in the last year gate syllabus from IIT Bombay, when they released that notification in the syllabus, they mentioned particularly about transformer vector groups. Actually, in previous years, we don't have that vector group term, particularly in transformer in the machines syllabus. But in the last year, they mentioned vector group. But anyhow, last year this year we did not got any question from vector group. But there is a chance we should know clearly about vector groups. That we see tomorrow, and today we see EMF equation of transformer. Before this question, see some EMF equation. Right. EMF equation. EMF equation. Already we have seen this is in single phase transformer. Here also same, no change. Here also same, but while writing, you should know this term. Keep in mind, whatever you calculated in single phase efficiency, regulation, same will come in three phase. But while calculating, take care for three phase transformer. The most of the students will do mistakes in three phase only. They know calculation, but they will do still mistake. So I will show you where most of the people will do mistakes in the numerical. So first listen this EMF equation. First, in single phase transformer, what is EMF induced in windings E1, E2? E1 equal to 4.44 Bm AN F N1. Okay. Similarly, E2 is what? Same equation. 4.44 Bm AN F N2. Then in single phase transformers, what is the voltage rating given always? E1 by E2. E1 by E2. Okay. In single phase transformer, what is the transformation ratio always? N2 by N1. Directly you can write. That is equal to E2 by E1. Directly you can write in single phase transformer. And this is equal to K. Transformation ratio we indicate. In single phase transformers it is. But if it is three phase transformer, what is the EMF equation? Same equation. Same equation. E1 equal to, first write, see, 4.44 Bm AN F and N1. While writing this E1 and N1, you should mention E1 phase, because in three phase, now the voltages will become two different types, like phase voltages and line voltages, based on the type of connection, delta or star. Based on delta or star, it will change now. That's why EMF equation always valid for phase voltage, not line voltage. This equation valid for phase. So the number of turns N1 also you should write N1 phase. Why N1 phase? Suppose primary delta, secondary star. Now in the primary we have three phases A, B, C. Total turns on primary is N1. Then if you write directly N1, that is blunder. You should write in this N1 per phase. Suppose total turns are 300. Then how many turns per phase? 100 only you have to write, not total 300 turns. EMF equation is valid for phase only. Okay, remember this point. EMF equation valid for phase voltage only. Similarly, E2. E2 phase equal to same equation, 4.44 Bm AN F En2 per phase. Okay, only difference is that phase you should mention. That's it. Next, in three phase transformer, what is the voltage rating given always? Line or phase? So if you see any numerical or on the nameplate of transformer, they will give the rating like this. See, for example, given 11 kV by 33 kV transformer, and connection also mentioned delta star. 11 kV by 33 kV delta star transformer. What is that rating indicates here? This 11 kV by 33 kV indicates primary line voltage divided by secondary line voltage based on given connection. So what is the voltage rating always given on the three-phase transformer? Primary and secondary line voltages. Induced EMF only, primary and secondary line voltages based on connection. Okay. However, we have primary side, secondary side in single phase, same as it is, but they are line voltages here. Keep in mind line voltages. Next, second point is how to write transformation ratio in three-phase transformer. So they given some rating. Here they given rating E1 by E2. K is what? E2 by E1. Directly you can substitute. But in three-phase transformer, can you write directly 33 by 11 here directly? E2 by E1. No, that is again blunder. It is not correct. K is the transformation ratio. Remember, this is always phase voltage ratio. Means secondary phase voltage to the primary phase voltage. Not line voltages. Never write line voltages. Or secondary phase turns to the primary phase turns. Or primary line current, phase current to the secondary phase current. Everything phase only. Transformation ratio in three-phase transformer is always phase ratio. That may be voltage ratio, that may be turns ratio, that may be current ratio. Okay, remember these 2 points. Rating is always line voltages, and the transformation ratio is valid for phase voltage ratio or phase turns ratio. Okay, so first take up to this and make a note. Make a note below this. Note. Write the point. Note. Completed. See, because the EMF equation is valid for phase, no, not line. In each phase, based on number of turns, EMF induced. So the K also, whatever you are writing, the K also phase voltage by the secondary phase voltage by primary phase voltage only, not for line. K is always phase values only. K also valid for phase. So make a note. Note. So with this statement, I will give one question. You try to answer that one so that you can answer any type of question further with this point. So try to listen carefully this. Write the points at the same time simultaneously. Note. In three-phase transformer, the phase voltages the phase voltages the phase voltages remain same for all connections, remain same for all connections, but line voltages will change. Line voltages will change based on type of connection. Based on type of connection. In three-phase transformer, the phase voltages remain same for all connections. Phase voltage remains same for all connection means what? What are all connections? Total 4 connections we have: delta delta, delta star, star delta, star star. For any connection, phase voltage remains same, but line voltages only will change when you change the type of connection. So to understand this point, I will give one example. So try to answer. Your all doubts will be cleared in this. Just wait. So how to find phase voltage in the numerical you will see. The relation between phase and line you will see. You should know already it is. In delta connection, star connection, what are the relations of phase voltages and line voltages? That you should know. So again, anyhow, we'll see in the numerical. First, see the question. Write the question. A three-phase 11 kV by 33 kV delta star connected or delta star transformer is reconnected is reconnected as star delta, reconnected as star delta, then its rating is dash. Then its rating is dash. Answer, what is the new voltage rating of that connection? So first understand this. There is a three-phase transformer, primary initially delta connected, secondary star connected. There at that time voltage rating is this much, 11 kV by 33 kV. Primary 11 kV. What is that voltage rating? Always line voltages. Now same transformer opened and reconnected. The winding terminals only changed. No, how to change the delta to star? Open the three phases, connect in star. We know how to connect. How to connect in delta? Opposite polarities. How to connect in star? Same polarity to be joined at neutral. Like that, it is open and reconnected as star delta. Then what is the new voltage rate? Try to solve it. Is it will change or same first? The voltage rating will change or remain same? No, not same. Definitely it will change. Not 33 by 11. Don't take reverse directly. Not 33 by 11. It is some other rating you need to calculate. It is not same. It will change definitely. Definitely it will change. See here. See. Initially delta star connected. What is the rating given? 11 kV by 33 kV. Okay. Now what is the point I said previously? In a three-phase transformer, phase voltages remain same for all connections, but line voltages will change based on type of connection. Okay. Now given is this, a delta star transformer given and its rating is 11 by 33. These voltage rating given is what? Always line. So these are the line voltages. Now what you have to do is convert these line voltages first into phase voltages. Convert into phase. It is phase. How to convert into phase? So primary delta connected. In delta, what is the phase voltage? Always line voltage. So you should know all these points. Don't ask how it is again. In delta, phase voltage, line voltage, both are same. That you should know again already from network theory. There all these basics will come. Okay. Similarly, in star, what is the phase voltage? Always in star, line voltage by root 3. Okay, those who don't know, just take this equation enough. In star connection, phase voltage is line voltage by root 3. Now apply this here. Therefore, in delta, phase voltage equal to line voltage. So 11 kV only divided by secondary star connected. 33 kV is the line voltage. What is the phase voltage? Line voltage by root 3. Line voltage by root 3. 33 by root 3 kilovolts. Okay. 33 by root 3 kilovolts. This is the phase voltages. Primary phase voltage, secondary phase voltage. This phase voltage is same for all connections. Same for all connections. Maybe delta delta, delta star delta, or star star. Anything that is. Now, for what we need to give the rating in the question? Star delta. If it is star delta, what is the voltage rating? So see now. Therefore, first star delta, we need to find rating. Star delta. Now rating means you should tell rating again always in line only. You should tell the rating in line voltages. So we have the phase voltage here readily. If it is star delta connected, what is the line voltage? Tell me. Line voltage. In star, use the same relations. What is the line voltage now? Root 3 times of phase voltage. But in delta, what is line voltage? Equal to phase voltage. So we need star. Primary is star. So primary phase voltage 11 kV. Then what is the line voltage? 11 root 3 kilovolts divided by secondary delta. What is the line voltage in delta? Equal to phase voltage. What is the phase voltage here? 33 by root 3 kV. So keep this is as it is. And what the people will do is, so 11 root 3, and here root 3 is there, into root 3 divided by 33. So 3 root 3 into 3, 33. 33 by, this is equal to 33 by 33. People will do this. 33 by 33. Finally 1. This is the voltage rating. So here voltage rating was finally that value there they are not asking. So don't cancel all this and simply keep as it is these values. Don't solve, again it is. What is the primary voltage rating? 11 root 3 kilovolts. What is the secondary voltage rating? You can solve only the secondary side, 33 by root 3. You can write 11 root 3. So if you write finally 11 root 3 kilovolts, 1:1 transformer, you get 11 root 3 kilovolts, both having same voltage rating. Primary, secondary, same. This is the new rating of star delta. Like that, if they ask for delta delta, what is the voltage rating now? Tell me. If they ask for delta delta, what is the voltage rating? For any connection, phase voltage is same, no? Means for delta delta also same phase voltages. Now in delta, line voltage, phase voltage same. So directly this phase voltage you can write 11 kV by 33 by root 3 kV. This is the voltage rating for delta delta. Okay. Line voltage equal to phase voltage. Same I written here. Same as it is I written. Next, if they ask for star star. Now what is the voltage rating for star star? For star star also phase voltages are same. This is only same 11 kV by 33 by root 3. Now what is the star connection line voltage? Root 3 times phase voltage. So 11 root 3 divided by 33 by root 3 into root 3. So root 3 cancel, 33 kilovolts. So this is the voltage rating for star star. Now clear how to find voltage rating for different connections? All of you. Okay. So according to this point, in a three-phase transformer, the phase voltages remain same. See, phase, what is this? Why remains same? Okay, some of you asked why it is remains same. Because transformer is same, fixed. A phase, each phase having some fixed turns. Then what is the voltage in each phase? Same only, no? See, there is one transformer. Each phase voltage is same because the number of turns in each phase is fixed. So initially there is some voltage rating given. So that is we are converting to phase. So phase voltage is same whatever the connection you made. So that point I given. In a three-phase transformer, phase voltages remain same for all connections. But line voltages, line just now we calculated for different connections, line voltages is different. Line voltages will change based on type of connection. Now see the question. Given a three-phase 11 kV by 33 kV delta star transformer. Okay, some data given. Now this delta star transformer, primary delta, secondary star. Now what I will do is same transformer I will open, and primary side I will reconnect to star, and secondary star I will open and reconnect to delta. Now star delta it is. Then what is the voltage rating? To find that star delta voltage rating, what we did, the given line voltage first we converted into phase. For that you need these relations. You should know this. So in phase, what is the phase voltage in delta? Equal to line voltage. So 11 kV. In star, what is the phase voltage? Line voltage by root 3. So 33 by root 3. So this is same for all connections. Now for star delta, if you want star delta voltage rating, how to tell? Voltage rating always you should give in line only, no? Then what is the line voltage? Root 3 times the phase. Now where is the phase? This is 11 kV. So 11 root 3 kV divided by in delta, secondary delta. What is the line voltage? Equal to phase voltage. What is the phase voltage? 33 by root 3. So as it is I written. The same for remaining connections also. Clear? Yes, practically you can change connection, but not easy. Like this, whatever we are changing the easy calculation, like that you cannot change. Practical transformer is there. If you want to change the connection, you need to open the tank and you need to take that complete core and winding outside. Then change the internal connections. It is not easy to change. Okay. Yes, KVA rating same because same winding we are using. Same winding we are using. Nameplate. Okay, tomorrow I will show you nameplate because today that point didn't came. So once we start vector groups, before that I will show you nameplate. And I will explain what is there completely in the nameplate, all the terms. Okay. Okay. Anyhow, today we stop here. So already we saturate. Tomorrow we continue. Same timing.
Hello, sir.
Tell Tulasi.
Sir, 87F, sir.
Okay.
Sir, third point about bushings you told, sir. Sir, can you please explain about?
Bushings means these are insulators because internal windings, the copper wire directly you cannot take the outside. So through we place insulator and inside we have one metal pin. Through that we take outside, that is.
Okay.
So using bushings for to take the voltages or winding terminals outside simply.
Sir,
Just like insulator.
LV winding 6, HV winding 6 in three-phase transformer bank.
Because here we are using individual 3 single phase transformers, no?
Yes, sir.
And each single phase transformer having 2 LV terminals, 2 HV terminals.
Sir, but we are connecting one terminal.
Connecting when you are connecting, after coming outside only, no, you are connecting.
Okay. But in single three-phase transformer, it is internal connection.
Internally connected reduce, yes.
Okay. Sir, in 90F, sir. Sir, first point, can you please?
In case of 3-phase transformer bank, if one of the phase gets fault, still it is suitable to supply continuity to the loads by using open delta.
Open delta connection, sir.
Because in case of this, suppose initially delta connected, primary delta, secondary delta. Suppose suddenly one of the transformer problem got. Then the remaining 2 transformers still working healthy. Okay. Still you can operate in open delta and you can supply. That is possible. And you will get proper supply only, and that is stable only. But if you take 3-phase transformer, single 3-phase transformer, how the 3 phases magnetically connected, kada?
Yes, sir.
As it is magnetically connected, if one phase fault occurred, balance will not come in the magnetic circuit.
But in single 3-phase transformer,
there magnetic circuit is different. No, there is no problem of unbalance. Okay, primary, secondary for each phase balanced. Same core, that is, and that current will not, phase A current will not touch with phase C current. They are individual.
Okay. But so in single 3-phase transformer, there is a magnetic connection.
Yes, magnetic unbalance will come.
Okay. Thank you, sir.
Sir, hello.
Dinesh, tell me.
Sir, in shell type transformer, sir. Due to like a single phase transformer, sir, due to the harmonic current, the harmonic flux is created, sir.
Okay,
and due to that flux, the current is induced.
Okay.
Voltage and the current flow, and so therefore, sir, due to this third harmonic current, Sir, the input current is peaky and the output is sinusoidal, sir.
Okay, I understand. You are saying due to that phi 3, E3 should produce and I3 will come. That I3 will produce again phi 3. That phi 3 will cancel this phi 3. Okay.
Okay. Yes, sir.
But I3 will not flow first. Star connection. Getting?
No, sir.
Star connection. How I3 will flow? Initial, just now, today itself we have seen in a star when I3 will flow. When neutral is grounded.
Only grounded. Okay.
But
Okay.
we are not grounding, na?
Yes, yes, sir.
Okay.
Yes, getting, sir.
Good evening, sir. Sir, ATF.
Amit. Vikram, tell me.
ATF, sir.
80?
ATF.
Ah.
Sir, how the delta connection guarantees the sinusoidal shape?
Because whatever primary or secondary, suppose primary delta directly, no problem, no? Primary delta, no problem, no? With this. If
Yes, sir.
primary is delta, directly there is a third harmonic current here, then directly
sir.
EMF induced always sinusoidal, okay? Now let us take star delta, for example. Delta, delta, delta star, both side primary is there, delta, no problem. And let us take star delta, okay? Now primary side star, what is the current flowing? Sinusoidal. Then what is the flux produced? Flat top. Then what is EMF induced? Peaky wave. So this EMF will be there in both primary and secondary, no? But
Yes, sir.
on secondary, when there is E3, there is third harmonic current. Same flux is there, same flux linking to both windings. Okay?
Yes, sir.
Now, when there is third harmonic EMF in secondary winding, immediately third harmonic current will circulate. Now, what that third harmonic current will do? It will produce a phi 3 or not?
Yes,
Now,
sir.
this phi 3 will cancel the previous phi 3 or not?
Yes, sir.
Then what is the resultant flux in the core finally?
Sinusoidal.
That's why.
Got it, sir. Thank you, sir.
Okay. Ayyappan.
Sir, the open delta connection.
Open delta.
Open delta connection, one transformer get failure.
Uh,
And get out in the how to load is unbalancing. Sir.
Balanced. We will see the in separate open delta topic is there, no? There I will show.
Okay, sir.
Good evening, sir. Sir,
Tell
in 68F, while we are taking IMU graph, a magnetizing current graph, there is a
60?
third 8,
60?
right? 8. Yesterday's.
Okay.
Not this one, sir. IMU graph we drawn. In the third harmonic, further we drawn graph from starting from negative half cycle, sir.
That is due to third harmonic in reverse direction is flowing.
What's
Third harmonic current is reverse direction, no?
how is it reverse?
Third harmonic current, I1 is flowing in this direction. Then how third harmonic current will come? Due to E3 in the reverse direction.
Okay.
Okay.
Okay. Sir, sir, afternoon, I asked one doubt in Telegram, sir.
Which one?
Sir, how that 400 is to 200 is to 200?
That vector,
Yes,
whenever
sir.
there
How
is
should
dot notation when indicated, you no need to consider directly with dot polarity, you can add the voltages there. No need to take again angles.
Sir, they indicated two cores, no, sir. How there are two different cores or cores
No
or
problem. No
same?
problem. Whatever they winding, they are connected in series only. No, whatever the codes, they given directly voltages there. Then what is the direct calculation only? Whatever the codes, winding voltage they indicated there. Then directly that voltage you can utilize to find the resultant.
Yes, sir. Thank you, sir.
Okay.
Sir, in 72 Fs.
Good evening.
Okay.
Sir, in this I3 will be 0 no sir in this ungrounded.
I3, yes, I3 0.
అంటే ఇప్పుడు ఇక్కడ జీరో సీక్వెన్స్ కాంపోనెంట్ కరెంట్స్ ఉండవు కానీ జీరో సీక్వెన్స్ ఈఎం వోల్టేజ్ ఉంటుందా సార్ దీంట్లో?
Yes, EMF will be there. For current closed path required, no?
సార్ నెక్స్ట్ పేజ్ సార్. సార్ మీరు ఇట్లా రాస్తున్నారా సార్ ఈవెన్ యాంగిల్ 0 ప్లస్ ఈవెన్ యాంగిల్ -120 అని అట్లా? అది ఈ కేసులో అంటే ఈ ఫిగర్ లో 72 ఫిగర్ లో అది సపరేటివ్ పొలారిటీలో ఉన్నప్పుడు అప్పుడు ఈవెన్ యాంగిల్ 0 మైనస్
అలానే తీసుకోవచ్చు. అందుకే మనం మైనస్ రాసేది కూడా సబ్ట్రాక్టివ్ కదా, VAN మైనస్ VBN.
అంటే అప్పుడు ఇక్కడ సమ్ ఆఫ్ బ్యాలెన్స్డ్ వోల్టేజెస్ 0 అవ్వదా సార్?
ఇక్కడ అవుతుంది, సమ్ ఆఫ్ వోల్టేజెస్ 0నే కదా. ఇఫ్ యూ యాడ్ సెపరేట్లీ ఆల్ ద వోల్టేజెస్, E1 at an angle 0 plus E1 at an angle -120 plus E1 at an angle -240 యాడ్ చేయండి.
ఇక్కడ యాడ్ చేస్తే 0 అవుతుంది సార్, కానీ ఇది సబ్ట్రాక్టివ్ పొలారిటీ కదా సార్.
అందుకే మనం ఎందుకు సబ్ట్రాక్టివ్ కనెక్ట్ చేస్తున్నాం? సపోజ్ సబ్ట్రాక్టివ్ కనెక్ట్ చేయకపోతే VAB ఏమవుతుంది చెక్ చేయవచ్చు సార్. VAN ప్లస్ VBN అవుతుంది. అప్పుడు ఏమవుతుంది చెక్ చేయండి ఒకసారి. E1 at an angle 0 plus E1 at an angle -120. వాట్ ఈస్ ద సమ్ ఆఫ్ దీస్ టూ నౌ? క్యాలిక్యులేట్ చేయండి. క్యాలిక్యులేట్ చేసి చెక్ చేయండి.
సార్ మళ్ళీ ఇంకోటి ఎయిర్ కి హై రిలక్టెన్స్ ఉంటది అన్నారు సార్, అంటే ఏమన్నా రీజన్
ఏం లేదు, మెటీరియల్ కాన్సెప్టే కదా. సో ఫ్లక్స్ ఆల్వేస్ ప్రిఫర్స్ లో రిలక్టెన్స్ పాత్. సో విచ్ వన్ విల్ హ్యావ్ లో రిలక్టెన్స్? ఎయిర్ ఉంటుందా ఆర్ మెటీరియల్ ఉంటుందా? ఫెర్రోమాగ్నెటిక్ మెటీరియల్. ఫెర్రోమాగ్నెటిక్ విల్ హ్యావ్ లో రిలక్టెన్స్, సో ఇట్ విల్ ఫ్లో దేర్ ఓన్లీ. If there is no availability, then it will go in air only.
సార్ మళ్ళీ ఎఫిషియన్సీకి కరెంట్ కి గ్రాఫ్ గీసినప్పుడు మాక్సిమం పాయింట్ వచ్చిన తర్వాత అది మళ్ళీ డిక్రీజ్ అవుతుంది కదా సార్? అంటే ఏమన్నా రీజన్ ఉందా సార్ ఎందుకు మళ్ళీ డిక్రీజ్ అవుతుంది? మామూలుగా అక్కడ maximum అంటే సాచురేషన్ పాయింట్.
Not like that. Maximum efficiency is at both copper equal to iron loss, no?
Yes,
both equal. Now further if you increase any load, current increase అయ్యే కొద్ది ఇంకా లాసెస్ ఏమవుతుంది? I2R లాస్ ఇంక్రీజ్ అవుతుంది కదా, అంటే ఎఫిషియన్సీ డిక్రీజ్ అవుతుంది కదా అప్పుడు.
మ్యాథమెటికల్ గానే తీసుకోవాలా సార్?
yes.
Sir, good evening sir.
Tell me Rakesh.
Sir, today's first question sir, something around 77 like that, which will produce harmonic current, third harmonic current. Yes sir, this one sir. Sir, like how third harmonic current will come to primary sir, second option అంటే స్టార్ గ్రౌండ్ చేశారు కదా, అక్కడికి ఎట్లా వస్తుంది సార్?
అంటే we have to assume in this case third option or second option?
Sir, firstly like question అనేది, yes sir, క్వశ్చన్ అనేది వాడు లైక్ అంటే రెండు ఫేజ్ ప్రైమరీ సెకండరీలో థర్డ్ హార్మోనిక్ కరెంట్ అనేది ఉండాలా? ఇస్ దట్ క్వశ్చన్ కరెక్ట్ సార్? అంటే నేను అనేది కరెక్టేనా?
దట్ ఇస్ సేమ్.
ఓకే సార్. సెకండ్ ఆప్షన్ హౌ సార్, లైక్ ప్రైమరీలో ఎలా వస్తుంది థర్డ్ ఫేజ్ కరెంట్?
సో ప్రైమరీ when possible we have to assume that source is already neutral grounded. Okay, we have to consider this. Then when there is a థర్డ్ హార్మోనిక్ కరెంట్ ఆన్ ప్రైమరీ, వెన్ ఎప్పుడు ఉంటుంది? స్టార్ న్యూట్రల్ గ్రౌండింగ్ అయ్యి ఉంటేనే థర్డ్ హార్మోనిక్ కరెంట్ పాత్ ఉంటుంది. ఓకే, బట్ ఇన్ ద ఫస్ట్ రిమైనింగ్ ఆప్షన్స్ CD there is no third harmonic current primary side. And primary side there is a, in first option there is a current, but secondary there is no current kada, neutral ungrounded. Like neutral must be grounded here.
Okay, individual check చేసుకోవాలా సార్?
Yes.
ఓకే సార్. నెక్స్ట్ క్వశ్చన్ సార్, ఇప్పుడు రాండమ్ గా క్వశ్చన్ లో ఏ రేట్ ఏ వోల్టేజ్ అని ఇచ్చినాడు అనుకో, 100 volts 200 volts ఇచ్చినాడు అనుకో, అది లైన్ వోల్టేజ్ తీసుకోవాలా ఫేజ్ వోల్టేజ్ తీసుకోవాలా సార్? మేబీ ఇన్ ఎనీ మెషిన్స్ లైక్ ఇండక్షన్ మెషిన్స్ లో అయినా ఇక్కడ
జనరల్లీ సింగిల్ ఫేజ్ అయితే నో ఫేజ్ లైన్, ఓన్లీ ఫేజ్ వోల్టేజ్, దట్ ఈస్ సింగిల్ ఫేజ్ లో. ఓన్లీ ఇన్ 3 phase transformers based on connection you have to take the numericals tomorrow చూద్దాం. There you will get.
One more thing. Yes sir. ఓపెన్ డెల్టా కనెక్షన్ అని అన్నారు కదా సార్ ఇప్పుడు ఇంతకు ముందు. అందులో అంటే ఓపెన్ డెల్టా కనెక్షన్ అంటే నో లోడ్ అని తీసుకోవచ్చా సార్? అంటే నో లోడ్ డెల్టా కనెక్టెడ్ విత్ నో లోడ్ అని.
ఓపెన్ డెల్టా అంటే డెల్టా కనెక్టెడ్ ట్రాన్స్ఫార్మర్ ఒక ఫేజ్ ఓపెన్ అయితే మనం దాన్ని ఓపెన్ డెల్టా అంటాం. అది లోడ్ ఉండొచ్చు, లైన్ లోడ్ లేకపోవచ్చు. సో సపరేట్ ఆ టాపిక్ వచ్చేటప్పుడు చూపిస్తాం.
ఓకే ఓకే సార్, థ్యాంక్ యూ సార్.
ఓకే.
Hello, sir.
Abdul Rahman.
Yes, sir. Sir, 85F, sir.
85.
Sir, star delta means IMF will be sinusoidal, sir.
Star delta means EMF sinusoidal. Yes, sinusoidal.
What is the purpose of switch 2 will be open in delta?
Because generally delta will provide path for third harmonic current. No?
Yes, sir.
But whenever you open S2, is there any closed path here? No.
No.
Then how third harmonic will flow? It cannot flow, no?
Oh, yes.
When there is no third harmonic current, what is the shape of flux? Flat top.
Patent. Yes.
Yes.
Thanks.
Okay.
Sir.
Yeah.
Sir, in the same question, sir, second one, sir, we have only third harmonic. Then third harmonic also is a sinusoidal, sir. If the answer is like sinusoidal wave with the third harmonic frequency, means it's correct.
Okay. Right on.
Sir, page 76F. Sir, please a bit go back and again come to this page. I need to get that out.
Which one?
Sir, the supply is sinusoidal supply, na sir. So E should be E1 plus E2 plus E3 plus E4, na sir. Next page na go, sir.
E should be?
This is the induced EMF, sir.
Yes, EMF induced in each phase, A, B, C. So
sir,
that is non-sinusoidal, no?
That
E1 plus E3 plus E5, that is we are writing.
Okay, that's peaky, sir. Sir, I need to clarify this. Why we are not getting even harmonics, sir? Before you have said, but I didn't get. I'm not
E1?
connecting that.
E1?
EA equal to E1 plus E3 plus E5 plus E7. Only odd, not even. Why, sir?
Because what is the nature of EMF or what? So according to Fourier series analysis, if any signal is non-sinusoidal but symmetrical, whatever EMF we are getting, that is symmetrical only, no, like this. Then any signal symmetrical means there will be having only odd harmonics. We will consider only odd harmonics.
Sir, here we are getting peaky wave, sir, in this.
Peaky wave. Symmetrical, positive, negative, same.
Sir, reason for peak is in current. Sir, one more, sir, it's clear. Sir, the current which should, if the current is sinusoidal, then the flux is flat topped and that is peaky. EMF is peaky. Which current should be that, sir? I mu or I naught or I1?
I mu, because which is responsible for flux and EMF? I mu only, no?
I mu only, sir.
That is magnetizing.
Sir, but in questions it's not mentioning that, no, sir. Directly we are taking I mu, but from supply we'll get I mu plus IW plus
in the some of the questions, yes, I have seen. They don't give properly. They will ask current drawn from supply. That's it.
Yes, sir.
Then we have to consider like that only. That is okay.
Okay, sir. Page 92F.
92.
92F. Not sir. Page 82F. 82F. 82 done. Yeah. Just now explain, sir. That source we have star, so it will go to that.
Yes.
It's clear, sir. Sir, 85, sir. First. This also clear. Sir, one more point you have said, sir. In delta, if primary or secondary is delta, then third harmonic will be zero. Third harmonic current. Then why, sir? Either this or this. If we have delta in primary, we have absence of third harmonics in secondary also. Why so, sir?
Because if primary is delta directly, what is the current in the phase? Peaky. Then what is the flux produced there itself?
Sir, please explain it, sir. I'm not
Whenever
getting.
there is delta on primary,
Okay, sir. Delta on primary.
source is sinusoidal always.
Okay,
So
sinusoidal.
current is sine.
Sine.
Then what is EMF induced according? First initially flux flow is
Okay,
flat
okay.
top.
Flat top.
Peaky.
EMF is peaky.
Now immediately as EMF peaky, third harmonic current will circulate.
Yes.
Now it will produce phi 3. It will cancel the actual phi 3. Then
Yes.
overall flux will be there itself sinusoidal, and then finally steady state EMF sinusoidal.
Okay, this is clear. Then if we have star on, no, don't rub it, sir. Now if we have star, then how that will be in that one thing also 530? I mean EMF is sinusoidal.
If primary star,
if delta is primary side, sir. Secondary side is star.
Primary side?
The secondary side is star, sir. Without grounded.
Delta star.
Delta star.
Once primary delta, now you no need to consider secondary also.
Why like that, sir? I'm asking that
because
only.
Flux whatever produced due to primary, it will link both the windings, no?
Yes.
Then what is the flux going to secondary? Sinusoidal.
No, sir. We can understand separate. Like in delta, I3 is 0. In star, I3 is not 0. But when we are both combining, you are telling that if any one of is there, then in both I3 will be 0.
Because the winding, both windings are there on the same core. If any one winding also able to produce third harmonic current, on the same core, the third harmonic flux is there, that will cancel out.
How it will cancel out? I mean
that phi 3
point. I understood the statement. How it will cancel out?
According to Lenz law only, no?
Lenz law. But there is no flowing of that I3 in star, na, sir. Without
primary delta is there, no?
How we will get phi 3 then? You said that that flux developed in the core will cancel out that flux. Means secondary side flux. To get that secondary side flux, first we need to have that flow of I3 in the star, na, sir.
See, not there. Primary delta producing third harmonic current.
Yes, sir.
Now it will produce a phi 3 or not?
Yes, sir.
Now this phi 3 will cancel the actual previous phi 3, which is cause for this or not?
Yeah, in primary side, sir. Yes, it will cancel out. But in secondary side also there is one similar phi 3.
Don't think. Primary, secondary, both on same core, no?
Oh.
What is iron for both same? Already in the iron phi 3 cancelled. Then how I phi 3 will go to secondary?
Yes, now cleared.
Okay.
Sir, that delta, sir. That delta में एक connection अगर reverse दिए तो एक problem आप बोले थे मुझे.
Delta connection.
Delta connection. One of the winding polarity test
one
अपन
of the
opposite.
phase is reverse.
Sir, please वो open कर. Sir, मेरे को different value 1.6 times of evil कैसा आ रहा है sir?
नहीं आता ना.
Up 2 times this one. Sir, यहाँ पे minus E1.
minus E1. उसके बाद प्लस आ
सर
जाएगा.
आप KVL अप्लाई करो सर उसमें.
So
आप अप्लाई करो सर.
This is let plus
minus okay. Sir, minus E1 plus E1 minus 120
minus E1
plus E1 at an angle
minus 120
minus E1 at an angle minus 240
minus E1 at an angle
minus 240 अगर उसमें से minus commonly इसको 1.6 आ रहा था सर.
check once.
यहाँ पे प्रॉब्लम क्या है बोले तो यहाँ पे आप नीचे सेकंड इक्वेशन लिखे ना सर. E1 at an angle 0 minus E1 at an angle minus 120 माइनस यहाँ थर्ड टर्म को माइनस लेना है और थर्ड टर्म को प्लस आता है.
नहीं ऐसे भी 2 आया ना वैल्यू. ये भी 2 ही है. चेक करना एक बार कैलकुलेशन.
नहीं सर आप साइन देख लो सर. ये 240 एंगल का है ना सर.
Okay,
Upper
maybe
minus.
so you are see somebody will take a minus, it is arrow is touching minus, so you take arrow in this direction, इससे क्या हुआ?
सिर्फ साइंस चेंज होते सर.
हाँ अभी suppose I take an arrow now like this, suppose third harmonic current flowing like this.
हाँ वो इक्वेशन में प्लस माइनस प्लस हो जाता.
हाँ वो सेम वही हो जाएगा,
लेकिन यहाँ
सेम
पे
आंसर तो
प्लस
आएगा.
माइनस माइनस है सर, आप देख रहे हैं. आई मीन मैं नहीं बता सक रहा हूँ यहाँ से. ऊपर एक इक्वेशन को वन वन बोल के डालो, ब्लू कलर में लिखे सो.
ऊपर कौन सा?
ये हाँ वही इक्वेशन को वन बोल के, वन इक्वेशन वन.
हाँ इक्वेशन 1.
नीचे आप रेड कलर से लिखे नहीं, इक्वेशन 2 उसके नीचे उसके नीचे उसके नीचे सर. हाँ हाँ ये उस ऊपर जरा एक स्टेप. हाँ वो सर इक्वेशन 1 इक्वेशन 2 में थर्ड टर्म का साइन ऑपोजिट है सर.
Equation 1 minus here, minus E1 at an angle minus 240. ये भी minus E1
माइनस है. हाँ अपन अपन डायरेक्शन ऑपोजिट ले बोल के वैसा है. अब ये डायरेक्शन एक क्लॉकवाइज लेना, एंटी क्लॉक ले तो प्लस माइनस प्लस आना, प्लस माइनस प्लस.
E1 at an angle 0 plus E1 at an angle minus 240. You take any way, चेक करना एक बार दो केसेस में भी इसका सम कितना है, सेम आ जाएगा.
नो सर इस आप करे सो 2 आ रहा, मैं करे सो 1.6 आ रहा, इसलिए
नहीं ये इक्वेशन 1 वही ना, इसका वैल्यू कितना है इक्वेशन 1 का?
1.6 आ रहा है सर.
नहीं वो 2 आ रहा है, चेक करना एक बार, चेक करके देखना कैलकुलेटर.
ओके मैं आप दूसरे डॉट से टर्न करो, मैं 2 मिनट.
ओके tell me.
Sir, note 2 ఒకసారి ఓపెన్ చేయరా సార్, డిఫరెన్స్ బిట్వీన్ ద 3-phase transformer and the single 3-phase transformer.
Page number?
Page number I don't know sir.
చెప్పు.
దానిలో note 2 చూపియరా సార్, note 2. సార్ ఇక్కడ మనము సింగిల్ ఫేజ్ 3 టైమ్స్ తీసుకుంటున్నాం కదా సార్, 3 phase. సార్
3 సింగిల్ ఫేజ్ ట్రాన్స్ఫార్మర్.
సింగిల్ ఫేజ్ ట్రాన్స్ఫార్మర్ తీసుకున్నప్పుడు దాని సైజ్ ఇంక్రీజ్ అవ్వదా సార్?
సైజ్ ఇంక్రీజ్ అవుతుంది కానీ మనకి ట్రాన్స్పోర్టేషన్ ఈజీ కదా ఈచ్ వన్.
3 phase ట్రాన్స్ఫార్మర్ కి దీనికి
ఈ పర్టికులర్ సపోజ్ ఈ హిల్ ఏరియాస్ లో మనం ట్రాన్స్ఫార్మర్ ఇన్స్టాల్ చేయాలంటే ఏది ఈజీ? ఒక బిగ్ ట్రాన్స్ఫార్మర్ ఈజీనా ఆర్ 3 స్మాల్ ట్రాన్స్ఫార్మర్స్ క్యారీ చేయడం ఈజీనా? అందుకే మనం అది మేబీ సైజ్ ఇంక్రీజ్, ఓవరాల్ సైజ్ ఇంక్రీజ్ కానీ క్యారీ ఇక్కడ ఇంపార్టెంట్ కదా మనకి.
ఓకే సార్ ఇది దాని వల్ల ట్రాన్స్పోర్ట్ కోసం వల్లనే ఇక్కడ ఇట్లా యూజ్ చేస్తారా, లేకపోతే అంటే ట్రాన్స్ఫార్మర్స్ కి కానీ ఏం ప్రాబ్లం లేకుండా ఉంటుందని ఇట్లా చేస్తాము?
సేమ్ అది డ్యామేజ్ అవ్వకుండా తీసుకెళ్ళొచ్చు కదా స్మాల్ అయితే. అదే బిగ్ అయితే మేబీ అది డ్రాప్ అయిపోవచ్చు బికాస్ రోడ్ సపోజ్ బాగాలేకపోతే. అండ్ వన్ మోర్ మెయింటెనెన్స్, ఎప్పుడైనా ట్రాన్స్ఫార్మర్ ఏదో ఒక ఫేజ్ లో ప్రాబ్లం వచ్చింది, ఆ ట్రాన్స్ఫార్మర్ ని రిపేర్ కి తీసుకురావాలి మళ్ళీ. సో ఇలా మెయింటెనెన్స్ చేయడం కష్టం కదా బిగ్ ట్రాన్స్ఫార్మర్ అయితే.
సార్ ఇన్ హైదరాబాద్ లో ఒక్కొక్క ఏరియాకి మనము సింగిల్ ఫేజ్ 3 యూజ్ చేస్తామా, లేకపోతే 3 phase యూజ్ చేస్తామా?
నో 3 phase ట్రాన్స్ఫార్మర్ డైరెక్ట్.
అంటే ఇక్కడ వెదర్ కండిషన్ చేంజ్ అయినప్పుడు ఫుల్ రెయిన్ అలా వచ్చినప్పుడు ట్రాన్స్ఫార్మర్స్ అనేది బర్న్ అవుతాయి కదా సార్?
బర్న్ అంటే బర్న్ కాదు, అది ఐసోలేటర్ అయ్యి ఓపెన్ అయిపోతాయి, అంటే జస్ట్ ప్రొటెక్షన్ ఉంటది కదా మనకి. ఏం కాదు ట్రాన్స్ఫార్మర్, మోస్ట్లీ ఫ్యూజెస్ డ్యామేజ్ అవుతాయి ఆర్ బ్రేకర్స్ ఓపెన్ అవుతాయి, దట్స్ ఇట్. ట్రాన్స్ఫార్మర్ ఫాల్ట్ అంటే అది వెరీ రేర్, మోస్ట్లీ అన్బ్యాలెన్స్డ్ కండిషన్స్ లో ఏమైనా ట్రాన్స్ఫార్మర్ 10 to 12 షార్ట్ సర్క్యూట్ అయితే అది ఓపెన్ అవుతుంది, ఆ టైంలో ట్రాన్స్ఫార్మర్ చేంజ్ చేయాలి.
అంటే
చాలా rare.
విలేజెస్ లో కానీ రేర్ కదా సార్ అసలు ట్రాన్స్ఫార్మర్స్ అనేటివి అట్లా అంటే డిస్టర్బెన్స్ కాకుండా అట్లా ఉండడం చాలా రేర్ కదా సార్. అందుకే సిటీలోకి దానికే
Yes.
అట్లా యూజ్ చేస్తారా అని.
Yes, yes.
ఓకే సార్.
Hello, sir.
Tell Dhanvi.
Sir, could you go to star connected winding, sir? So first thing I had this first topic is effect
Your
of
why-
non-linearity in 350.
Page number?
So, sir, first today's first page, sir. Yes, sir. It start with yes, sir. In this, sir. Sir, there is no path for the third harmonic currents to flow, sir. Which so then can we consider this will be an unbalanced condition, sir?
No, not unbalanced. This is third harmonic current. No, the unbalance means due to fundamental currents. If loads are different, then unbalanced.
So, but actually in star connected, if there's a path for neutral, if there's some unbalancing, then neutral currents will flow, sir. Sir, but there's
Okay,
no
that
path
is
for
completely protection point of view you are considering. We are not talking about that. Only third harmonic current we are considering. That path required, na?
No, path required, sir. But here, then if we consider phase voltage, sir, they are not sinusoidal, sir. So can't we say that it's a unbalanced situation?
Unbalance is, your voice is not properly audible to me.
Is it audible now, sir?
You message me, I will tell you, because not audible clearly your voice.
Yes, sir.
It is coming little broadly voice. Tell me now.
Yes, sir. In this phase voltage only, like there E1 at an angle 0 plus E3 at an angle 0. So there are VAN plus VBN plus VCN will not be equal to 0. So can't we say that the phase voltage is unbalanced? So
VAN, VBN plus VCN is not 0?
Here only. Yes, sir. It's not equal to 0.
Yes,
left side only will be equal, sir.
Not equal to 0 means due to third harmonic voltages, it is not equal to 0.
So then we can say this is unbalanced.
Yes. Balanced means the sum should be 0, but when there is third harmonic, it is okay under unbalanced condition only. Right. Right.
సార్ లైక్ ఎస్టర్డేస్ డౌట్ సార్, మీరు స్టడీ స్టేట్ ఇంకా ట్రాన్సియెంట్ స్టేట్ అన్నారు కదా సార్, లైక్ ఇన్పుట్ వోల్టేజ్ అనేది. సో ఆఫ్టర్ స్టడీ స్టేట్ ఇప్పుడు ఇన్పుట్ అనేది పీకి అయింది అనుకో, అప్పుడు కరెస్పాండింగ్ ఫ్లక్స్ అండ్ ఈఎంఎఫ్ వేవ్స్ ఎలా ఉంటాయి సార్, ఒక్కసారి చెప్పగలరా?
Input is peaky.
Input is peaky, sir. Flux and EMF ఏమవుతుంది?
How input is peaky? Current. If current is peaky, then flux will be sinusoidal, EMF also sinusoidal.
Current is peaky.
Flux sinusoidal, EMF also sinusoidal.
Okay, like peaky input అనేది ఇవ్వలేమా సార్ ఎప్పుడు?
No, peaky we cannot supply, no. We don't have source. Peaky source is there.
No, we don't have.
That's why source is sinusoidal and it will generate third harmonic current automatically generate.
Okay. So input current అనేది peaky ఉంటే we'll get a flux and EMF sinusoidal.
Sinusoidal.
Okay. Input current అంటే like magnetizing current అన్న సార్ ఇక్కడ?
Yes, because the flux related means that is only the current we have to consider.
Okay. Thank you, sir.
Sir 1.6 ही चाह रहा है सर. Same. सर कैल्सी में 2 बार टाइप करा सर.
Single separate. Put bracket separately and calculate.
वही चीज करा दे. सर आप वही पेज था सर. सर आप ये एट एन एंगल -240 है ना सर?
फर्स्ट माइनस C1
माइनस नहीं, आप प्लस ले लो, कुछ भी ना होता.
E1 at an angle 0
minus E1 at an angle minus 120
minus E1 at an angle minus 120
plus E1 at an angle minus 240. ये
minus
है ना सर
240.
KVL एक्चुअल आप यहाँ पे माइनस लिए थर्ड टर्म को
ओके, जो भी लिए सेम तो आना
हाँ
है
उसके
चेक करना.
हाँ ये करो सर आप 1.6 आता.
एक मिनट. No, 2 at an angle 60 इसका आंसर. 2 at an angle 60 आ रहा है.
सर इसके ऊपर एक क्वेश्चन है ना सर. नहीं सर ठीक है आप 2 बार करें मैं भी 2 बार करा लेकिन
चेक किया.
ठीक है सर इसके ऊपर एक प्रॉब्लम था ना सर.
कौन सा? वो इस वन.
हाँ हाँ सर इसके अंदर नहीं है. अब ट्रांसफार्मर 2 बोल के बोला, अगर वो ट्रांसफार्मर 1 या ट्रांसफार्मर 3 ऐसा कुछ भी दे दो
कुछ भी सेम एनी वन ट्रांसफार्मर इफ यू रिवर्स सेम आंसर.
सर ऊपर क्वेश्चन में क्या है कि क्लॉकवाइज लिया, नीचे क्या है कि एंटी क्लॉकवाइज लिया सर. ए बी बी सी सी है. आप गौर करें सर. ये ऊपर क्या है कि
वो के व्हाटएवर इट इज ए बी देन इसके बाद बी सी उसके बाद सी है. ये भी वैसा ही है ना. फर्स्ट ये भी.
ओके सर अगर ऑपोजिट नेगेटिव सीक्वेंस में दे तो सर जब चेंज होता है.
नहीं सेम. प्राइमरी एंड सेकेंडरी मस्ट बी सेम व्हाटएवर.
मतलब इनपुट में अपन कौन सा सीक्वेंस दिया आउटपुट भी वही सीक्वेंस.
वही आएगा.
उसको जो अपन पॉजिटिव सीक्वेंस बोलते हैं उसके ऑपोजिट रहता है नेगेटिव सीक्वेंस.
यस
नहीं ये क्लॉकवाइज
generally if you give primary side this anti-clockwise ना this is we consider as negative sequence. Generally ABC positive लेते हैं ना हम. ABC positive direction. Clockwise is a positive sequence.
Sir, I have solved again. It's again 1.6 only, sir.
नहीं.
Okay, let it be, sir. Thank you, sir.
Okay, good night. I'm closing for today.
Sir,
Tomorrow.
Sir, how many classes we may expect again after this?
Mostly up to Monday, I think.
Monday, sir. Okay.
Sir.
Hello, sir.
మీరు లైక్ వోల్టేజ్ పీకి ఇవ్వనప్పుడు ఇన్పుట్ కరెంట్ ఎలా ఇస్తాం సార్ పీకి?
వోల్టేజ్
ఇంతకుముందు వోల్టేజ్ పీకి ఇవ్వలేమని అన్నారు కదా సార్.
వోల్టేజ్ లేదు కదా పీకి.
కరెంట్ పీకి ఉంటుందా సార్?
ఏది ఉండదు. అన్ని సైనూసాయిడల్ సోర్స్ అనేది.
దెన్ మళ్ళా పీకి ఇచ్చినప్పుడు మీరు ఫ్లక్స్ ఇంకా ఈఎంఎఫ్ సైనూసాయిడల్ వస్తుంది అన్నారు కదా సార్. అది ఎలా వస్తుంది మళ్ళా?
పీకి మనం ఇవ్వట్లేదు. ఆ పీకి అనేది అదే జనరేట్ అవుతుంది కదా కరెంట్ ఫ్లో అవడం వల్ల.
ఓకే, కరెంట్ ఫ్లో ఆఫ్టర్ స్టడీ స్టేట్ సంథింగ్ ట్రాన్సియెంట్ లో పీకి అనేది మనకి ఏర్పడుతుంది. సో దాని వల్ల
సైనూసాయిడల్ కన్వర్ట్ అయిపోతుంది.
Okay. So no sub source is given like peaky for current or voltage.
Source always sinusoidal only.
Okay. Thank you, sir.
Balakrishna. Yugosri.
సార్ మాకు కాలేజ్లో ఉన్నప్పుడు మిషన్స్ అంతా పంచా చెప్పలేదు సార్. అంత టఫ్ వస్తుందా సార్ పేపర్ అంటే?
టఫ్ ఏం లేదు, అంతా ఈజీనే. కాకపోతే ఫస్ట్ టైం మనకి అసలు ఏమీ తెలియకుండా వింటే ఫస్ట్ టైం అలానే ఉంటుంది కదా. కాలేజ్
మాకు అంత మంచిగా చెప్పలేదు సార్ కాలేజ్ లో ఉన్నప్పుడు, అందుకనేసి.
ఏ కాలేజ్ అయినా సేమ్ అమ్మ, ఇక్కడే కాదు ఏ కాలేజ్ అయినా ఒకటే. సో ఎవ్రీథింగ్ వి షుడ్ లర్న్. కంప్లీటెడా మీరు?
కంప్లీటెడ్, జస్ట్ ఇది అడగడానికి.
No problem. Now concentrate because 1 year is there. No, almost 6 months is there. 6-7 months.
Okay.
So properly utilize this and try to learn. So this is enough to get a good rank.
Sir. Sir, yesterday's class, sir, I didn't remember page number, but before non-linearity of curve, sir. Before we have started non-linearity topic now, sir.
बताना क्या है उसमें?
सर वो क्वेश्चन ऐसा है, HV साइड LV साइड के R1 X1 R2 X2 दिए सर.
ओके.
अगर अपने को लोड वोल्टेज सेम 220, अब आज भी एक करें ना सर, 220 रेटिंग क्या की 2200/220 है.
Yes, yes.
V2 should be maintained 220, then V1 should be what बोलते बोले सर.
Oh, yes.
तो इसके अंदर अपन एक मेथड क्या कि आप V1 new is equal to V1 old plus per unit regulation into V1 new old बोल के बोले, लेकिन अपन KVL डायरेक्ट अप्लाई करके भी कर सकते बोले ना सर. तो मैं ट्राई करा सर, जरा डिफरेंट रीडिंग्स आ रहे सर.
If you transfer V2 to primary side, what is the voltage? V2 by K.
V2 by K, yes sir.
वो तो load voltage. How much voltage? Whatever they asked, that much voltage we should keep there.
Sir, I'll tell the procedure, sir, how I solved. First, he had given V2.
No, you just send in Telegram. I will check. That is easy. Send in Telegram
Sir,
that photo. I will check.
I'm not using Telegram, sir. Only WhatsApp. Only WhatsApp, sir. Can I WhatsApp you?
WhatsApp तो उस वो नंबर पे नहीं है.
नहीं सर, Telegram नहीं है सर मेरे को.
इंस्टॉल कर लेना. नहीं करेगा.
नहीं सर, WhatsApp एक बस है सर.
और मेल को भेज देना. मेल को भेज देना.
हाँ, मेल को भेज देता हूँ सर. आप
skb2588@gmail.com.
skb skb 2588. ठीक है. Thank you, sir.
Balakrishna. Quickly, Balakrishnan. Rajit.
సార్
Tell.
సార్ మీరు ఇది థర్డ్ హార్మోనిక్ రివర్స్ డైరెక్షన్ అన్నారు కదా సార్, అది ఎలా అర్థం అవ్వట్లేదు.
ఇక్కడ మనకి E3 ఇండ్యూస్ అవ్వడం వల్లే కదా థర్డ్ హార్మోనిక్.
yes sir.
ఇప్పుడు E3 ఏ డైరెక్షన్? E3 will cause a current opposite to fundamental current, no?
Fundamental, yes sir.
అందుకే కరెంట్ రివర్స్ లో ఫ్లో అవుతుంది.
Okay.
Rajit.
So not clear, sir. I did it by mistake.
Okay. I'm closing for today.
Hello.
Balakrishnan, tell me.
Sir, I made out yesterday, sir.
Okay, it is not audible properly. No, your signal is fluctuating.
Fine.
No, not audible. You message me, I will check.